In this presentation we discuss the dynamics of rigid bodies where we deal with the following topics. We will start with the description and the classification of the rotation of rigid bodies about a fixed axis, by solving the equation of motion of the bodies under the influence of torques due to external forces applied on them. In the study of this kind of motion we introduce the general form of the moment of inertia of a rotating rigid body with respect to its axis of rotation, and investigate some special cases related to the symmetries of the geometry of the bodies of uniform density. Then we will present two types of pendulums, the torsion pendulum and the physical pendulum, where we analyze their oscillatory motion in the terms of torque and moment of inertia and provide some examples for their applications in the everyday life. We also discuss the motion of a sphere and a cylinder rolling down an inclined plane, determine their instantaneous acceleration and kinetic energy in the terms of their radii and moment of inertia, and examine the role of rolling friction in their motion. As a next topic, we study the rotation of rigid bodies about their free axes where their axis of rotation is not fixed, and determine the relation between free rotation, the axes of symmetry of the body, and the properties of its moment of inertia. Then we will talk about the rotation of force-free spinning tops where the torque produced by the net forces acting on the top vanishes, and investigate what kind of motion the axis of rotation of the top performs while spinning about this axis. We finish this presentation with the discussion on heavy spinning tops where the torque produced by the external forces acting in the top, normally gravity, does not vanish. We examine the complex motion its axis of rotation as well, and mention some of the natural phenomena and applications in the everyday life where the effects related to spinning tops are important. When we studied the kinematics of rigid bodies we saw that rigid bodies can be considered as special systems of point masses for which the laws of conservation of momentum and angular momentum hold. These laws completely determine the motion of a rigid body, since they can be described by the second-order differential equations of 6 scalar variables, that is the components of the momentum and the angular momentum of the body, and the free motion of a rigid body has just 6 degrees of freedom associated with the translation and the rotation of the body in space. The motion of a rigid body, for example a devil stick thrown in the air, is generally the composition of a translational motion and a rotational motion. In most of the cases the analysis of such a motion is very complicated. We will therefore consider only some special motions. We do not examine translational motion since it can be considered as a part of the mechanics of point masses due to the law of center of mass. We will only deal with rotational motion starting with its simplest case, the rotation of a rigid body about a fixed axis. Let us choose the z-axis as the axis of rotation of a rigid body and let phi denote the angle of rotation about the axis measured between the points p and p' in space. Because the angular velocity vector omega is aligned with the axis of rotation, its length is equal to its z-component. We already saw that the z-component of the angular momentum L of the body with respect to the z-axis is given by the moment of inertia I of the body with respect to the axis of rotation, times the z-component of the angular velocity vector omega of the rotating body. The moment of inertia I of the body can be approximated by the sum of n mass elements mi of the body, times the square their distances di from the axis of rotation from I equals 1 to n, where n tends to infinity. The distance di of a mass element at the point pi can be determined from the length of the position vector r pointing from a reference point O on the z-axis to the point p, and the z-coordinate of the point A if the origin of the z-axis is at the point O on the axis. By applying the definition of the angular velocity omega, the z-component of the angular momentum L can be written as the moment of inertia I, times the derivative of the rotation angle phi with respect to the time t. Then the law of conservation of angular momentum states that the derivative of Lz, that is the time derivative of I times omega z, is equal to the z-component of the torque with respect to the axis of rotation produced by the net force of all the external forces acting on the body. Here the external forces consist of the free forces exerted on the body which are given, and the constrained forces keeping the axis of rotation fixed which are unknown. Nevertheless, we can assume that the constrained forces are exerted at the fixed axis of rotation and the torque produced by them vanishes. As a result, tau z in the right-hand side of the differential equation is the z-component of the torque produced by the free external forces acting on the body. Because the moment of inertia I of the body does not depend on time, we can write the left-hand side of the equation as I times the time derivative of omega z, that is I times the second-order time derivative of the angle of rotation phi. Here the second-order time derivative of the angle of rotation is the angular acceleration alpha of the rotating body. Then we conclude that the equation of motion of a rigid body rotating about a fixed axis is the following. The moment of inertia I of the body with respect to its axis of rotation times the second-order derivative of its angle of rotation phi about the axis with respect to the time t, is equal to the z-component of the torque produced by the free external forces acting on the body. This equation is formally equivalent to the equation of motion of a mass point m along a straight line chosen as the x-axis, which states that the mass m times the second-order derivative of the displacement x of the point mass along the line with respect to the time t, is equal to the x component of the force F acting on the point mass. Let us discuss some special cases of rigid rotation here. If the right-hand side of the equation of motion of a rotating rigid body about a fixed axis is equal to 0, that is the z component of the torque tau vanishes, then in the simplest case the time derivative of the rotation angle phi, that is the z component of the angular velocity omega, is constant. In other words, if the torque produced by the free external forces acting on a rigid body vanishes, then the body rotates at a constant angular velocity about its fixed axis of rotation. Indeed, if a flywheel of large moment of inertia, which has a vertical axle with ball bearings holding it in its position, is set in motion by hands, then the angular velocity of the spinning wheel is almost constant. The slow decrease in its velocity is due to the torque produced by the frictional forces between the axle of the flywheel and the ball bearings. If we impose the initial condition such that we measure the angle of rotation phi from the initial angle of the orientation of the rigid body, that is the initial angle phi naught, is 0, then the integration of the first-order differential equations gives the angle phi as the product of the angular velocity omega z of the rotation and the time t. By comparing this result with the equation stating that the distance s covered by a point mass moving along the x-axis at a constant velocity vx is equal to vx times the time t, we can state that the rotation of a rigid body at a constant angular velocity about a fixed axis corresponds to the uniform motion of a point mass along a straight line. Another simple case is when the z component of the torque tau is constant, that is the angular acceleration of the rotating body is constant. Then the equation of motion can be written in the form stating that the second-order time derivative of the angle phi, which is also equal to the angular acceleration alpha, is given by the ratio of tau z and the moment of inertia I. Because the right-hand side is constant, we talk about a uniformly accelerating rotation of the body, stating that if the torque produced by the free external forces acting on a rigid body is constant, then the body rotates with a uniform angular acceleration about its fixed axis of rotation. For the initial values of vanishing angle phi and angular velocity omega at the initial time t naught, the integration of the equation of motion gives an expression stating that the time derivative of the angle phi is equal to alpha times the time t. By integrating this equation we obtain an expression for the angle of rotation, where phi is given by 1 over 2 times alpha times t squared, that is 1 over 2 times the ratio of tau z to I, times t squared. This solution shows that the equation of motion for a rigid body rotating with a uniform angular acceleration about a fixed axis is formally equivalent to the equation of motion for the uniformly accelerating rectilinear motion of a point mass, where the later tells us that the distance s covered by the point mass is equal to 1 over 2 times the acceleration a of the point mass times the square of the time t. We can study the uniformly accelerating rotation in an experiment by using an apparatus, where two discs of mass md are attached to a horizontal rod and the middle of the rod is joined with an axle mounted on supports allowing its rotation about a vertical axis. The distance between the discs and the axis of rotation is denoted by d. A thread is tightly wound around a pool of radius are attached to the vertical axle, and it passes over a fixed pulley with its end tied to the weight G of mass m held at a fixed position. The weight G acting on its support is given by its mass m times the gravitational acceleration g. Another spool of radius 2 times r is also attached to the axle under the first spool, which can also be used in the experiment. If we set the weight G free by removing its support, then the falling weight will drive the spool fixed on the axle and the system of the discs, and the rod starts to rotate. We can measure the time t1 taken to the first complete rotation of the system, that is when its angle of rotation is equal to 2 pi. Then we will find that during the time intervals 2 times t1, 3 times t1 and so on, the system performs 4, 9 and so on complete rotation, as seen in the table where the duration of motion shown in the first line and the second one contains the number of rotations n of the system during the time 2 times t1, 3 times t1 and so on. This result demonstrates that the angle of rotation phi is directly proportional to the square of the time t, that is the system performs a uniformly accelerating rotation. The torque is produced on the system by the force F, which has the same magnitude as the weight G, since the fixed pulley simply redirects the force G applied on the thread by the falling weight. As a result, tau z is equal to the product of the magnitude of the weight G and the radius r of the first spool on the axle. If we use the second spool of radius 2 times the radius r, then we double the torque driving the system, which also doubles the angular acceleration alpha of the system. If we do not change the torque and it remains constant, but we increase the distance d of the discs from the axis of rotation to 2 times d, then the moment of inertia of the rotating system becomes about 4 times its original value. As a result, the angular velocity of the rotation reduces to about the quarter of its original value. Now we determine the energy of a rotating rigid body about a fixed axis. The kinetic energy of a rigid body of mass m approximated by a system of n-point masses mi is given by the sum of the kinetic energies of the individual point masses, that is 1/2 times the sum of the mass mi times the square of the velocity vi of the point mass mi from I equals 1 to n. This formula describes the general case, and if we consider rigid rotation, that is where each point mass approximating the rigid body has the same angular velocity about the z-axis, then we can write the velocity vi of the point mass I as the product of its distance di from the axis of rotation times the angular velocity omega of the point mass about the z-axis. For the sake of brevity we drop the index z of omega, since the angular velocity vector pointing in the direction of the z-axis has vanishing components in the x and y directions. By substituting this relation into the general formula of the kinetic energy, we obtain an expression stating that the kinetic energy is equal to 1/2 times the sum of the product of mi and di squared from I equals 1 to n, times omega squared. Here we recognize the sum as the moment of inertia I of the body with respect to the fixed axis of rotation. Then we can introduce the rotational energy of a rigid body rotating about a fixed axis defined by 1/2 times the moment of inertia I with respect to the axis of rotation, times the angular velocity omega of the rotation. Because the center of mass of the body does not perform translation in the case of the rotation about a fixed axis, the kinetic energy of the rigid body is equal to its rotational energy. We also present another important relation for rigid rotation, stating that the work delta W done on the rigid body rotating through a small angle delta phi about the z-axis is equal to the z component of the torque tau produced by the free external forces acting on the body, times the angle delta phi. The infinitesimal version of this formula tells us that the differential of the work W done on the body rotating through an infinitesimal angle d phi is given by the product of tau z and d phi. Now we can apply the work energy theorem for the experiment producing an uniformly accelerating rotation of the system of 2 disks attached to a rod. The theorem states that the change in the kinetic energy of the complete apparatus in the experiment is equal to the work done by the weight g after it is set free. When we set the weight G free and it covers the distance z during the time t, the work done by the moving weight is equal to G times the distance z, or the mass m of the weight times the gravitational acceleration g times z. The increase in the kinetic energy of the rotating system and the moving weight is given by 1/2 times the moment of inertia I of the rotating system times its angular velocity omega at the time t, plus 1/2 times the mass m times the square of the velocity v of the weight at the time t. Here we suppose that the mass of the pulley is very small and its moment of inertia is negligible. Then the expression described here must be equal to the work done by the weight, as shown by this equation. Here the velocity v of the weight is equal to the time derivative of its z-coordinate, which can be inserted into the derivative of the whole equation with respect to the time t. Then we obtain the equation stating that I times omega times the time derivative of omega, plus m times v times the time derivative of v, is equal to m times g times v. We can assume that the angular velocity of the rotating system is given by the ratio of the velocity of the weight to the radius of the spool driven by the moving weight, that is the velocity v is equal to the radius or times the angular velocity omega. We can also replace the product of the mass m and the gravitational acceleration g by the weight G in the equation, and write that I times omega times the time derivative of omega, plus m times omega times r squared times the time derivative of omega, is equal to G times r times omega. Because the right-hand side of the equation is equal to the torque tau z produced by the force F times the angular velocity omega, after dividing the equation by omega we obtain the expression stating that the sum of I and m times r squared, times the time derivative of omega is equal to tau z. Then we can express the time derivative of omega, that is the angular acceleration alpha, as the ratio of torque z produced on the rotating system by the moving weight to the sum of the moment of inertia I of the system, and the mass m of the weight times the square of the radius r of the spool attached to the vertical axle of the rotating system. This formula shows that the angular acceleration of the system is less than the value tau z over I derived in the previous description of the experiment. The difference between the two expressions is due to the fact that the weight g of the body suspended on the thread produces not only rotational motion but also accelerates the body itself. However, if the mass m of the body is 10 grams, the mass of the discs md is 50 grams, the radius r of the spool is 2 centimeters, and the distance d of the discs from the axis of rotation is 20 centimeters, then we can determine the angular acceleration by using the original formula. For these values, m times r squared is equal to 40 grams square centimeter, and the moment of inertia given by 2 times md squared is equal to 4 times 10 to 4 grams square centimeter. Hence we conclude that the ratio of the torque to the moment of inertia I is still a good approximation for the angular acceleration in this setup. As already seen, if no external torque is produced on a rigid body spinning about a fixed axis, then the body rotates with a constant angular velocity. Hence its angular momentum Lz with respect to the axis of rotation chosen as the z-axis, given by the product of the moment of inertia I of the rigid body with respect to the axis of rotation and the angular velocity omega of the body, is also constant. Its kinetic energy, given by 1 over 2 times the moment of inertia I, times the square of the angular velocity omega, is constant as well. We also demonstrated that if the moment of inertia changes in a rotating non-rigid system, then the angular velocity of the system also changes. For example, if a student sitting on a revolving stool already set in motion suddenly outstretches her arms holding a pair of weights, then she increases her moment of inertia and her spinning slows down. We used this experiment to demonstrate the law of conservation of angular momentum itself, stating that the product of the original values I1 and omega1 of the moment of inertia and the angular velocity is equal to the product of the new values I2 and omega2 of the moment of inertia and the angular velocity. Here the angular velocity omega2 can be expressed by the ratio of the moment of inertia I1 to the moment of inertia I2, times the angular velocity omega1. Nevertheless, the kinetic energy of the system does not remain constant, since the difference between 1 over 2 times I1 times omega1 squared and 1 over 2 times I2 times omega2 squared does not vanish. If we substitute the expression obtained for omega2 into the second term, then we obtain 1 over 2 times I1 times 1 minus the ratio of I1 to I2, times omega1 squared. As the law of conservation of energy formulated in the work energy theorem telling us, this expression is equal to the work W of the internal forces, which does not vanish if the final moments of inertia I1 and I2 are different. For example, in the experiment shown in the photos, it is equal to the negative work done against the centripetal force by the student while extending her arms with the weights. We already mentioned that there is a formal analogy between the rotational motion like the one seen in the photos, and the rectilinear motion like a ball falling in the ground or oscillating at the end of a spring. If the rotation angle phi of the spinning rigid body corresponds to the linear distance x covered by the moving point-like body, the angular velocity omega of the rotation to the velocity v of the point mass, the torque tau z causing the rotation of the rigid body to the force Fx changing the state of motion of the point mass, and the moment of inertia I of the rigid body with respect to its axis of rotation to the mass m of the point-like body performing the rectilinear motion, then we can recognize this formal analogy between several equations. As formally established, the equation of motion of the rotating motion states that the moment of inertia I of a rotating rigid body with respect to its axis of rotation chosen as the z-axis times the second-order derivative of the rotation angle phi of the body about the axis with respect to the time t, is equal to the z component of the torque tau produced by the forces acting on the body, and it corresponds to the equation of motion of the rectilinear motion of a point mass m, stating that the mass m times the second-order derivative of the distance x covered by the point mass along a straight line chosen as the x-axis with respect to the time t, is equal to the force Fx acting on the point mass in the x direction. There is a similar correspondence between the expressions for the kinetic energy in the case of the two types of motion. The kinetic energy of a rotating rigid body is given by 1 over 2 times the moment of inertia I of the body with respect to the axis of rotation, times the square of the angular velocity omega of the body. The kinetic energy for the rectilinear motion of a point mass m has the same form. It is given by 1 over 2 times the mass m times the square of the velocity v of the point-like body. The work done in rotating motion and rectilinear motion has also its analog forms. The work delta W done during a small rotation of a rigid body is equal to the torque Z producing the rotation, times the angle of rotation delta phi, whereas the work delta W done during a small displacement of the point mass along the x-axis is equal to the force F producing the displacement, times the displacement delta x. In this table we summarize the quantities, expressions and equations which have formal analogies in the case of the two types of motion. The left-hand column of the table shows quantities and equations describing the rectilinear motion of a point mass or a particle-like body along the x-axis, whereas the right-hand column contains the corresponding expressions for the rotational motion of a rigid body about the z-axis. In the first line we specify the fundamental kinematic variables for the two kinds of motion, the Cartesian coordinate x measuring the distance covered by a point mass moving along the x-axis for the rectilinear motion, and the polar angle phi measuring the angle of rotation of a rigid body about the z-axis. The derivatives of these fundamental kinematic variables with respect to time are the velocity Vx of a point mass along the x-axis, and the angular velocity omega z of a rigid body rotating about the z-axis. Similarly, the acceleration ax of a point mass along the x-axis is defined by the time derivative of its velocity Vx, that is the second-order derivative of its coordinate x with respect to time, and the corresponding quantity is the angular acceleration alpha of the rotating rigid body defined by the time derivative of its angular velocity omega z, that is the second-order time derivative of its rotation angle phi. The fundamental property of a point mass performing a rectilinear motion from the viewpoint of dynamics is its mass m, and this property for a rotating rigid body is the moment of inertia I of the body with respect to the axis of rotation. The later can be written as the sum of the product of the point masses mi approximating the body and the square of their distance di from the axis of rotation. The effect changing the state of motion of a point mass traveling along the x-axis is represented by the force Fx acting on the point mass in the direction of the x-axis. The corresponding quantity for a rigid body is the z component of the torque tau with respect to the axis of rotation causing for the body to rotate along the fixed z-axis. As we have already seen, the corresponding equations of motion tells us that the mass m of the point mass times the second-order time derivative of the x-coordinate is equal to the force Fx acting on the point mass in the x direction, and that the moment of inertia I of a rigid body times the second-order time derivative of its angle of rotation phi is equal to the z component of the torque tau rotating the body about the fixed z-axis. Another fundamental dynamical quantity describing the rectilinear motion of a point mass is its momentum or linear momentum p in the x direction defined by the product of its mass m and its velocity vx in the x direction. Its corresponding quantity for a rigid body rotating about the z-axis is the z component of the angular momentum L of the body with respect to the z-axis, which is the product of the moment of inertia I of the body with respect to the axis of rotation and the z component of the angular velocity omega of the body. The law of conservation of momentum tells us that the time derivative of the momentum px of a point mass in the x direction is equal to the force Fx acting on the point mass in the x direction. Its analog is the law of conservation of angular momentum stating that the time derivative of the z component of the angular momentum L of a rigid body rotating about the z-axis is equal to the z component of the torque tau produced by the forces acting on the body. We also defined a quantity called impulse for a point mass under the influence of forces by the integral of the force Fx applied on the point mass in the x direction with respect to the time t from the initial time 0 to a given time tau. This definition can also be introduced for a rotating body in the form of the angular impulse acting on the body, which is given by the time integral of the z component of the torque tau over the time interval from 0 to tau. We have already shown the correspondence between the concept of infinitesimal work done during the two types of motion. The infinitesimal work dw done on the point mass by the force Fx acting in the x direction for the infinitesimal displacement dx of the point mass is equal to Fx times dx. Similarly, the infinitesimal work dw done on a rigid body by the torque z rotating it through the infinitesimal angle d phi is given by the product of tau z and d phi. By applying these equations we can also express the power for both kinds of motion. The power p of the force Fx acting on a point mass traveling with the velocity Vx along the x-axis is equal to Fx times Vx, whereas the power p of the z component of the torque rotating a rigid body about the z-axis with the angular velocity omega z is given by tau z times omega z. The formal analogy between the kinetic energies for the rectilinear motion and the rotating motion is already shown as well. The kinetic energy of a point mass m is defined by 1/2 times the mass m times the square of the velocity Vx of the point mass moving in the x direction. The same quantity for a rigid body rotating about the z-axis is equal to 1/2 times the moment of inertia I of the body with respect to the z-axis times the square of the z component of the angular velocity omega. We can also mention Hooke's law in the case of the one-dimensional motion of a point mass attached to a spring, stating that the restoring force Fx acting on a point mass is proportional to minus its displacement x measured from its equilibrium position, where the proportionality factor k is the spring constant. We can generalize Hooke's law to the z component of the torque produced on the rigid body by directional forces, and state that tau z can also be proportional to minus the angular displacement phi of the body about the z-axis, where the proportionality constant k is the torsional constant. The corresponding period t measured for a point mass m oscillating under the influence of forces following Hooke's law is given by 2 pi times the square root of the ratio of the mass m to the sprig constant. Similarly, the period t of the oscillation of a rigid body about its axis of rotation can be written as 2 pi times the square root of the ratio of the moment of inertia I of the body with respect to the axis of rotation to the torsional constant k. Let us consider a more general mathematical description of rigid rotation about a fixed axis, where a Cartesian coordinate system is attached to the axis of rotation such that its origin is located at the reference point O on the axis, and its z-axis is the axis of rotation. In the study on the mechanics of systems of point masses, we saw that the momentum of a rigid body approximated as the composition of mass elements, that is a rigid system of n point masses, can be written as the sum of the momenta pi of the individual point masses mi, that is the sum of the mass mi times the velocity vi of the point mass mi from I equals 1 to n. We also saw that the angular momentum L of the rigid body in such an approximation can be written as the sum of the angular momenta Li of the individual point masses mi, that is the sum of the mass mi, times the cross product of the position vector Ri of the point mass mi with respect to the reference point O and its velocity vi from I equals 1 to n. Similarly, the torque tau produced on the rigid body by forces acting on the body can also be expressed as the sum of the torques tau I produced on the individual point masses mi by the forces acting on them, that is the sum of the cross product of the position vector Ri of the point mass mi and the net force Fi acting on the point mass from I equals 1 to n. We already determined the scalar components of the momentum, the angular momentum, and the torque in these vector equations. Since the velocity vi of a rotating point mass mi is equal to its distance di from the z-axis times the angular velocity omega of the rigid body, the magnitude of the momentum pi of a rotating mass element mi is given by the mass mi times the distance di, times the angular velocity omega. This expression for the magnitude of the momentum pi can be used to determine the Cartesian coordinates of the momentum vector as the projections of the vector on the coordinate axes. However, we can also use a cylindrical coordinate system with the same z-axis due to the rotational symmetry of the motion. In this case the distance di is equal to the radial coordinate ρ of the cylindrical coordinate system as seen in the expression in the second line of the right-hand side of the equation. The different components of the momentum can be derived by projecting the momentum vector of this length onto the axes if the polar and azimuthal angles that describing the direction of the vector are known. The z component of the angular momentum Li of the point mass mi was also derived by applying the same procedure, where we use the relation stating that the distance di of the point mass mi from the axis of rotation is equal to the length of the position vector Ri of the point mass, times the cosine of the angle theta I measured between the direction of the position vector and the z-axis. As a result, the z component of the angular momentum Li was written as the mass mi times the square of the distance di, times the angular velocity omega in Cartesian coordinates. In a cylindrical coordinate system the distance di is replaced by the radial coordinate ρ, as seen in the second line. The other components of the angular momentum Li can be determined as well by projecting its vector onto the x and y axes and using trigonometric relations. Similar projections of the cross product of the position vector Ri and the force Fi gives the components of the torque tau I in the Cartesian and cylindrical coordinate systems. The rotation of a rigid body about the z-axis is determined by the components of the equation of motion stating that the time derivative of the angular momentum L of the body with respect to the z-axis is equal to the torque tau produced by the forces acting on the body. This vector equation representing the law of conservation of angular momentum consists of three scalar equations describing a motion with the degrees of freedom reduced by the constraint fixing the axis of rotation. The components of the vector equation are written both in Cartesian and cylindrical coordinates. We saw that the z component of this equation in the green boxes for both types of coordinate systems describes the rotational motion of the body about the z-axis. In Cartesian coordinates the two other components of the equation of motion are its x and y components, whereas in cylindrical coordinates we have the radial and azimuthal components of the vector equation denoted by the subscripts ρ and phi, respectively. The constraint forces exerted on the ball rings fixing the direction of the axis of rotation and the torques produced by the constraint forces can be determined from the other two components of the equation of motion shown in the yellow boxes, plus the law of conservation of momentum, where the later states that the time derivative of the momentum p of the center of mass of the body is equal to the net force F of all the forces, that is both the free and constraint forces acting on the body. By expanding the vector equation of the law either in Cartesian coordinates or cylindrical ones, the scalar equation can be arranged in the same group as the equations of the law of conservation of momentum shown in the yellow box. These five scalar equations written in both types of coordinates are called the kinetostatic equations of the rigid rotation, and they are used to determine the constraint forces and the torques produced by them. As the figure shows, each point of the rigid body rotating about the z-axis moves along a circular trajectory in a plane perpendicular to the z-axis, that is all the point masses approximating the body perform a planar motion parallel with the xy plane in the Cartesian coordinate system. Then the z component of the momentum p of the rigid body vanishes, and so does its time derivative in the law of conservation of momentum, which tells us that the z component of the net force F acting on the body is equal to 0. The latter indicates the balance between the free forces and the constrained forces fixing the position of the rotating body in the vertical direction. Now we generalize the calculation of the moment of inertia based on the approximation of rigid bodies with rigid systems of point masses. As already seen, the moment of inertia I of a rigid body with respect to the z-axis in the approximation using a system of n point masses is given by the sum of the mass mi of the point mass mi times the square of the distance di of the point mass from the z-axis. Here the square of the distance di is equal to the square of the x-coordinate of the position vector ri of the point mass, plus the square of the y-coordinate of the position vector. We also saw that the moment of inertia has the same role in the case of rotations about an axis as the mass for point-like bodies performing translational motion. Furthermore, this quantity depends on the distribution of the mass of a body with respect to the axis of rotation, as the formula shows. In the approximation using a rigid system of point masses, we can follow the same procedure as in the case of the calculation of the center of point mass of rigid bodies, where we consider the point masses as the mass elements delta mi, given by the average density ρ I of the mass element times the volume delta V I of the mass element. In the limiting case, the number n of the mass elements tends to infinity while their volume delta V I becomes the infinitesimal volume element dV shrinking to 0. For a realistic mass distribution represented by the density ρ of the body, the infinite sum converges and its limit will be a volume integral. Then the moment of inertia I of a rigid body of volume calligraphic V with respect to the z-axis can be written as the integral of the density ρ of the body, times the square of the distance d of the volume element in the integral from the axis of rotation, over the volume calligraphic V of the body. The square of the distance d in the integrand can be replaced by the sum of the square of the x-coordinate and the square of the y-coordinate, where the volume element is the function these Cartesian coordinates. As an example, we determine the moment of inertia of a homogeneous rod of length L and cross-sectional area Q with the uniform density ρ with respect to the z-axis perpendicular to the rod. In the first case, the axis passes through the center of mass C of the rod, and it passes through one of its ends in the second case. Here the center of mass C is at the middle of the homogeneous rod of constant density. Because the volume element dV of the rod can be written as the product of the cross-sectional area Q of the rod and the infinitesimal length dx measured along the rod, the moment of inertia I of the rod with respect to the axis passing through its center of mass is given by the integral of the density ρ of the rod, times the square of the distance x from the center of mass C, times the cross-sectional area Q with respect to the distance x from minus the length L over 2 to plus the length L over 2. Here ρ and Q are constants and the integral of x squared gives x cubed over 3 evaluated at the limits of the integral. As a result, we obtain ρ times Q, times the cube of L over 12, where we can use the relation for the density ρ of the rod expressed as the mass m of the rod over the cross-sectional area Q times the length L, and state that the moment of inertia of the rod with uniform density with respect to a perpendicular axis passing through its center of mass is equal to 1 over 12 times the mass m of the rod, times the square of its length L. If the axis of rotation passes through one of its end, then its moment of inertia I is given by the density ρ times the cross-sectional area Q, times the integral of the square of the distance x from the end which the axis passes through with respect to this distance from 0 to the length L. Here the integration gives L cubed over 3, and the moment of inertia I of the rod with respect to a perpendicular axis passing through one of its end is equal to 1 over 3 times its mass m times the square of its length L. In many cases, the moment of inertia I of a rigid body of mass m can be written as the mass m times the square of the radius of gyration k, where the body is replaced by the point mass m at the distance of the radius of gyration k from the axis of rotation. The results obtained for the homogeneous rod can be seen in the first line of this table showing the moment of inertia I of solids of uniform distribution of mass, that is of constant density with respect to different central axes. The third and fourth lines contains the moment of inertia of a cylinder of radius r and height h with respect to its axis of symmetry, which is equal to 1 over 2 times the mass m of the cylinder, times the square of the radius r, and with respect to a central axis perpendicular to the symmetry axis, which is equal to 1 over 4 times m times r squared, plus 1 over 12 times m times the square of the height h. In the first line of the second table we can see the moment of inertia I of an empty cylindrical shell of an arbitrary height with respect to its symmetry axis, where r1 and r2 are the exterior and interior radii of the shell. Here the moment of inertia is given by 1 over 12 times the mass m of the shell, times the sum of r1 squared and r2 squared. The second line shows the moment of inertia of a rectangular cuboid of length a, width b and height c with respect to the vertical central axis, which is equal to 1/12 times the mass m of the cuboid, times the sum of the square of its length a and the square of its width b. In the third line we can see the moment of inertia of a cube of side a with respect to any of its central axis parallel with its edges, which is given by 1/6 times the mass m of the cube times a squared. The first line in the last table shows the moments of inertia I of a sphere of radius r and a thin spherical shell of the same radius with respect to any of their central axes. The moment of inertia for the sphere is given by 2/5 times the mass m of the sphere times r squared, whereas I is equal to 2/3 times the mass m of the shell times r squared for thin spherical shell. In the second line we can see the moment of inertia of an ellipsoid with semi-axes a, b and c with respect to the central axis in the direction of the semi-axis c, which is given by 1/5 times the mass m of the ellipsoid, times the sum of a squared and b squared. The last example is the moment of inertia of a circular cone of radius r and arbitrary height with respect to its symmetry axis, which is equal to 3/10 times the mass m of the cone times r squared. Now we prove the Huygens-Steiner theorem on the rotation of rigid bodies about parallel axes, attributed to the polymath Christian Huygens, who also introduced the concept of moment of inertia, and later generalized by the Swiss mathematician Huygens-Steiner. Let us consider two parallel axes passing through the points A and C of a rigid body where C is the center of mass of the body. Here the figure shows the cross-section of the body in a plane intersecting both the points A and C. The axes passing through the points A and C are perpendicular to this plane. The axis passing through the center of mass C of a rigid body is also called the central axis of the body. Obviously, the central axis of a rigid body is not unique since its direction is arbitrary. Now the direction of the central axis has the same direction as the axis passing through the point A. We attach a Cartesian coordinate system to the point C such that its z-axis is the central axis of the body and the straight line connecting the points A and C is the x-axis. The distance between the two parallel axes is given by d, as seen in the figure. Let Ia denote the moment of inertia of the rigid body with respect to the axis passing through the point A. Similarly, Ic will denote the moment of inertia of the body with respect to its central axis, that is the axis passing through its center of mass C. We apply the approximation with a rigid system of point masses mi, where any point mass mi at the point P of the body has the coordinates xi and yi in the coordinate system attached to the central axis of the body. Here di denotes the distance between the point P and the central axis, and the distance between the point P and the axis passing through the point A is denoted by d bar I. Because the position of the point P is arbitrary within the body, these distances are always measured in the plane perpendicular to the parallel axes that intersects the point P. Then we can write the moment of inertia Ic of the body with respect to its central axis as the sum of the mass mi times the square of the distance di of the point mass from the central axis, from I equals 1 to the number of point masses n. This is equal to the sum of the mass mi times the sum of the square of the x-coordinate of the position of the point mass mi and the square of the y-coordinate of its position, from I equals 1 to n. Similarly, the moment of inertia Ia of the body with respect to the axis passing though the point A is given by the sum of the mass mi times the square of the distance d bar I of the point mass from the axis, from I equals 1 to n. Here the square of the distance d bar I can be expressed as the square of the difference between the xi coordinate and the distance d, plus the square of the yi coordinate. By removing the bracket we obtain the sum of mi times the sum of xi squared and yi squared from I equals 1 to n, plus d squared times the sum of mi from I equals 1 to n, minus 2 times d times the sum of mi times xi squared from I equals 1 to n. We can recognize the moment of inertia Ic in the first term in the right-hand side, whereas the sum in the second term gives the total mass of the system of point masses approximating the rigid body, that is the mass m of the body itself. Because the x-coordinate of the center of mass C of the body is given by 1 over the mass m times the sum of the mass mi times xi from I equals 1 to n, which vanishes in the coordinate system with the origin at the point C, the last term in the right-hand side also vanishes. This result can be summarized in the Huygens-Steiner theorem as follows: if Ic is the moment of inertia of a rigid body of mass m with respect to its central axis, that is an axis passing through the center of mass of the body, then the moment of inertia I of the body with respect to a parallel axis at the distance d from the central axis is given by the sum of the moment of inertia Ic and the product of the mass m and the square of the distance d. As an application of the theorem, let us calculate the moment of inertia of a rod of length L and mass m with a uniform density with respect to the axis passing through one of its end that is perpendicular to the rod. We saw that the moment of inertia c of the rod with respect to a perpendicular axis passing through its center of mass c is equal to 1 over 12 times the mass m of the rod times the square of its length L. Since the distance between the center of mass c of the rod and any of its end is the half of its length, the theorem states that the moment of inertia I is equal to 1 over m times L squared, plus m times the square of L over 2. Because the second term in the right-hand side of the equation can be written as 3 over 12 times m times L squared, the moment of inertia I of the rod can be written as 1 over 3 times the mass m times the square of the length L, as we expected. We consider a more general situation where the origin O of the Cartesian coordinate system used to describe the motion of the rotating rigid body is still located on the axis of rotation, but the later forms the angles alpha, beta, and gamma with the coordinate axes x, y, and z, respectively. Then the components of the unit vector E in the direction of axis of rotation are the cosines of the angles alpha, beta, and gamma that the vector makes with the coordinate axes, called direction cosines. We will determine the moment of inertia denoted by I sub alpha beta gamma of the rigid body with respect to the axis with the direction described by the angles alpha, beta, and gamma with respect to the coordinate axes. In the approximation applying a rigid system of n-point masses, any mass element of the body is represented by a point mass mi, which has the position vector Ri with respect to the origin O, where the components xi, yi and zi of the position vector describe the position of the point mass in space. Then the moment of inertia I sub alpha beta gamma is equal to the sum of the mass mi of the point mass mi times the square of the distance di of the point mass from the axis of rotation, from I equals 1 to n. If the point A denotes the projection of the position of the point mass mi onto the axis of rotation, the square of the distance di can be written as the square of the length of the position vector Ri minus the square of the distance between the origin O and the point A. Because the distance between the points A and O is given by the scalar product of the position vector Ri and the unit vector E, the square of the distance di between the point mass mi and the axis of rotation can be written as the sum of the squares of the components of the position vector, that is xi squared plus yi squared plus zi squared, minus the square of the scalar product of the two vectors written in terms of the coordinates of the vectors, that is the square of the quantity of xi times cosine alpha plus yi times cosine beta plus zi times cosine gamma. In the right-hand side of this equation we can separate the terms containing the square of the Cartesian coordinates from the terms containing the products of these coordinates. Then the first group of the terms is given by 1 minus the square of cosine alpha times xi squared, plus 1 minus the square of cosine beta times yi squared, plus 1 minus the square of cosine gamma times zi squared. Whereas the second group is given by minus 2 times xi times yi times cosine alpha times cosine beta, minus 2 times yi times zi times cosine beta times cosine gamma, minus 2 times zi times xi times cosine gamma times cosine alpha. Since the sum of the squares of the direction cosines is equal to 1, the first three terms forming the first group can be written as the sum of the square of cosine beta and the square of cosine gamma, times xi squared, plus the sum of the square of cosine alpha and the square of cosine gamma, times yi squared, plus the sum of the square of cosine alpha and the square of cosine beta, times zi squared. By removing the parentheses, regrouping the terms, and factoring out the squares of the direction cosines in the right-hand side, we obtain three terms, the sum of yi squared and zi squared, times the square of cosine alpha, plus the sum of zi squared and xi squared, times the square of cosine beta, plus the sum of xi squared and yi squared, times the square of cosine gamma. If we substitute this result into the original equation, then we can write the square of distance di of the point mass mi from the axis of rotation as 6 terms grouped with respect to the squares of the direction cosines and their mixed products. Now we insert this expression into the equation of the moment of inertia of the body with respect to the axis of rotation described by the angles alpha, beta, and gamma, and we write I sub alpha beta gamma as the following: the sum of mi times the sum of yi squared and zi squared, times the square of cosine alpha from I equals 1 to n, plus the sum of mi times the sum of zi squared and xi squared, times the square of cosine beta from I equals 1 to n, plus the sum of mi times the sum of xi squared and yi squared, times the square of cosine gamma from I equals 1 to n, minus 2 times the sum of mi times xi times yi times cosine alpha times cosine beta from I equals 1 to n, minus 2 times the sum of mi times yi times zi times cosine beta times cosine gamma from I equals 1 to n, minus 2 times the sum of mi times zi times xi times cosine gamma times cosine alpha from I equals 1 to n. It is a lengthy expression, but we introduce a set of notations for the multiplication factors containing the Cartesian coordinates to simplify the result. Then we conclude the following. The moment of the inertia I sub alpha beta gamma of a rigid body with respect to an axis passing through the point O in the direction determined by the angles alpha, beta, and gamma with respect to the axes of the coordinate system with the origin at the point O is given by I sub xx times the square of cosine alpha, plus I sub yy times the square of cosine beta, plus I sub zz times the square of cosine gamma, plus 2 times I sub xy times cosine alpha times cosine beta, plus 2 times I sub yz times cosine beta times cosine gamma, plus 2 times I sub zx times cosine gamma times cosine alpha. Here the quantity I sub xx given by the sum of mi times the sum of yi squared and zi squared from I equals 1 to n, is the moment of inertia of the body with respect to the x-axis of the coordinate system. The quantity I sub yy given by the sum of mi times the sum of zi squared and xi squared from I equals 1 to n, is the moment of inertia of the body with respect to the y-axis of the coordinate system. The quantity I sub zz given by the sum of mi times the sum of xi squared and yi squared from I equals 1 to n, is the moment of inertia of the body with respect to the z-axis of the coordinate system. The quantities I sub xy denoting minus the sum of mi times xi times yi from I equals 1 to n, I sub yz denoting minus the sum of mi times yi times zi from I equals 1 to n, and I sub zx denoting minus the sum of mi times zi times xi from I equals 1 to n are called products of inertia of the body with respect to the coordinate axes. Unlike the moments of inertia which are always positive, the products of inertia can be positive, negative or zero depending on the shape and orientation of the rigid body. They describe how the rotation of a body about one coordinate axis is affected by its shape and mass distribution with respect to another coordinate axis. If the distribution of mass is symmetric about a plane, then the product of inertia vanishes with respect to that plane. For example, I sub xy is equal to 0 if the mass distribution of the body is symmetric about either the xz plane or the yz plane. We note that another convention is also used for the definition of the products of inertia where the minus sign is not included in the definition, reversing the signs of the last three terms in the expression obtained for the moment of inertia I sub alpha beta gamma. In the general case, we define the moment of inertia of a rigid body by a volume integral which also holds for the moments of inertia with respect to the coordinate axes. By assuming that the rigid body has a continuous distribution of mass, the moments of inertia of the body with respect to the coordinate axes attached to the point O becomes volume integrals. For example, the moment of inertia I sub xx of the body with respect to the x-axis is given by the volume integral of the density ρ of the body times the sum of the square of the x-coordinate and the square of the y-coordinate with respect to the volume v over the volume calligraphic v of the body. Here the volume element dv in the integral can be expressed in terms of the Cartesian coordinates x, y and z. Similarly, the products of inertia become volume integrals as well. For example, I sub xy is given by minus the volume integral of the density ρ times the coordinate x times the coordinate y with respect to the volume v over the volume calligraphic v of the body. In order to illustrate the geometric interpretation of the expression obtained for the moment of inertia of a body with respect to an arbitrary axis, let us choose the location of the point P on the axis of rotation that passes through the point O in any direction described by the angles alpha, beta, and gamma with respect to the coordinate axes such that the distance between the points is equal to 1 over the square root of the moment of inertia I sub alpha beta gamma with respect to the axis of rotation. Here the moment of inertia is determined by the geometry and the distribution of mass of the body. If we project the point P onto the coordinate axes, then we obtain the triple key, eta, and theta, which can be used to describe the position of the point instead of its Cartesian coordinates. As the figure shows, the coordinate key can be written as the distance between the points O and P times cosine alpha, that is cosine alpha divided by the square root of I sub alpha beta gamma. Then cosine alpha is equal to key times the square root of I sub alpha beta gamma. Similarly, cosine beta can be expressed by eta times the square root of I sub alpha beta gamma, and cosine gamma by zeta times the square root of I sub alpha beta gamma. After having expressed the direction cosines in terms of the triplet, we can substitute them into the equation obtained for the moment of inertia I sub alpha beta gamma. This gives I sub xx times key squared times I sub alpha beta gamma, plus I sub yy times eta squared times I sub alpha beta gamma, plus I sub zz times zeta squared times I sub alpha beta gamma, plus 2 times I sub xy times key times eta times I sub alpha beta gamma, plus 2 times I sub yz times eta times zeta times I sub alpha beta gamma, plus 2 times I sub zx times zeta times key times I sub alpha beta gamma. Because each term in both the sides of the equation contains the quantity I sub alpha beta gamma, we can divide the equation by this quantity assuming that it is not zero. Then we obtain the equation stating that 1 is equal to I sub xx times k squared, plus I sub yy times zeta squared, plus I sub zz times zeta squared, plus 2 times I sub xy times k times zeta, plus 2 times I sub yz times zeta, plus 2 times I sub zx times zeta times k. This expression is the equation of a quadratic surface in terms of the coordinates k, eta, and zeta, where the surface is an ellipsoid. Indeed, the moment of inertia I sub alpha beta gamma defined by the sum of the point masses approximating the body times the square of their distances from the axis of rotation cannot be zero, apart from the cases of a single point mass or a dumbbell model of uniform distribution of mass if the axis of rotation is its symmetry axis. As a consequence of the non-vanishing expression of I sub alpha beta gamma, the quadratic surface cannot be hyperboloid or paraboloid, and we conclude that the equation obtained for I sub alpha beta gamma corresponds to the ellipsoid of inertia related to the point O. Let us consider the axis passing through the point O in the direction given by the angles alpha, beta and gamma with respect to the coordinate axes with the origin O. If the point P is the point of intersection of this axis and the ellipsoid, then the moment of inertia of the body with respect to the axis is given by 1 over the square of the distance between the points O and P. The three mutually perpendicular axes of symmetry of the ellipsoid of inertia that intersect at its center are called the principal axes of inertia. The moments of inertia of the body with respect to the principal axes are the principal moments of inertia of the body, and they are given as follows. The first principal moment of inertia denoted by I1 is equal to 1 over the square of the distance between the points O and capital A, where this distance is denoted by A as seen in the figure. Similarly, the second principal moment of inertia denoted by I2 is equal to 1 over the square of the distance between the points O and capital B, or 1 over the square of the distance B, and the third principal moment of inertia denoted by I3 is equal to 1 over the square of the distance between the points O and capital C, or 1 over the square of the distance C. If we consider the general case, these principal moments of inertia are not equal to each other. In fact, the minimum value of these principal moments is equal to the minimum value of the moment of inertia with respect to any axis passing through the point O. Similarly, the maximum value of these principal moments gives the maximum value of the moment of inertia with respect to any axis passing through the point O. In a special case where all the three principal moments of inertia are equal to each other, the ellipsoid of inertia becomes a sphere, that is, the moment of inertia of the body is the same with respect to any axis passing through the point O. If choose the principal axes of the ellipsoid of inertia as the coordinate axes passing through the point O, then this choice represents a coordinate transformation from the Cartesian coordinates x, y and z to the coordinate x bar, y bar and z bar. This means that we also transform the triplet key, eta and zeta to a new triplet key bar, eta bar and zeta bar. By applying this transformation, we can write the equation of ellipsoid of inertia in canonical form stating that the principal moment of inertia I1 times k bar squared, plus the principal moment of inertia I2 times zeta bar squared, plus the principal moment of inertia I3 times zeta bar squared is equal to 1. Or equivalently, k bar squared over the square of the distance A, plus eta bar squared over the square of the distance B, plus zeta bar squared over the square of the distance C is equal to 1. The products of inertia of a rigid body therefore vanish in the principal axis system of the ellipsoid of inertia associated with a rigid body with respect to a given point O. As a result, the moment of inertia I sub alpha beta gamma of a rigid body with respect to an axis passing through the point O in the direction described by the angles alpha, beta and gamma in the principal axis system is equal to the principal moment of inertia I1 times the square of cosine alpha, plus the principal moment of inertia I2 times the square of cosine beta, plus the principal moment of inertia I3 times the square of cosine gamma. Let us suppose that the point O is the center of mass of the rigid body. If the principal moments I1, I2 and I3 and the directions of the principal axes with respect to the body are known, that is 3 scalars and 3 angles are given, then the Huygens-Steiner theorem can be applied to calculate the moment of inertia of the body with respect to any axis. In the 3 tables of the moments of inertia shown before for different solids of uniform density, all the moments of inertia are the principal moments of inertia of the solids with respect to their center of mass. For example, the rectangular cuboid with the width A, the length b and the height c has the principal momenta given by 1 over 12 times the mass m of the cuboid times the sum of b squared and c squared, 1 over 12 times the mass m times the sum of c squared and a squared, and 1 over 12 times the mass m of the cuboid times the sum of a squared and b squared. If the width a is equal to the length b but they are not equal to the height c, then the first 2 principal momenta are equal to each other and different from the third one. Thus the ellipsoid of inertia is an ellipsoid of revolution about the principal axis parallel with the edge c of the cuboid. If the width a, the length b and the height c are equal to each other, then all the three principal moments of inertia of the cube are the same, and the ellipsoid of inertia of the solid is a sphere. We already saw that the kinetic energy of a rigid body rotating about the z-axis is given by the half of its moment of inertia with respect to the z-axis times the square of the angular velocity of the rotation. In the general case, the kinetic energy of a rigid body rotating about an axis given by the angles alpha, beta and gamma with the angular velocity omega is equal to 1/2 times the moment of inertia I sub alpha beta gamma, times omega squared. In the principal axis system of the body, the moment of inertia I sub alpha beta gamma reduced to I1 times the square of cosine alpha, plus I2 times the square of cosine beta, plus I3 times the square of cosine gamma. Then we can write the kinetic energy as 1/2 times the sum of I1 times omega squared times the square of cosine alpha, I2 times omega squared times the square of cosine beta, and I3 times omega squared times the square of cosine gamma. We already introduced the angular velocity vector omega, which is parallel with the axis of rotation and its length is equal to the angular velocity. As the figure shows, the components of this vector in the principal axis system are given by omega times cosine alpha, omega times cosine beta, and omega times cosine gamma. If we substitute these expressions into the kinetic energy of the rotating rigid body, then it can be written as 1/2 times the sum of the first principal moment of inertia I1 of the body times the square of the first component of its angular velocity omega, its second principal moment of inertia I2 times the square of the second component of the angular velocity omega, and its third principal moment of inertia I3 times the square of the third component of the angular velocity omega. This is the simple form of the rotational energy of the body expressed in its principal axis system with respect to a given point O. We can also express the kinetic energy of a rotating body in terms of its angular momentum L, if we decompose the latter in the principal axis system of the body, where the components of the angular momentum are equal to the product of the corresponding principal moments of inertia and components of the angular velocity vector. By expressing the components of the angular velocity from these equations and inserting the result into the equation obtained above, we can write the kinetic energy as 1/2 times the sum of the square of the first component of the angular momentum L over the first principal moment of inertia I1, the square of the second component of the angular momentum L over the second principal moment of inertia I2, and the square of the third component of the angular momentum L over the third principal moment of inertia I3. This form of the kinetic energy of a rotating body is also expressed in the principal axis system with respect to a given point O. As an illustration, we use the example of the rectangular cuboid again. If we substitute the principal moments of inertia for the cuboid into the equation of the kinetic energy, then we can write the latter as 1/24 times the mass m of the cuboid, times the sum of three terms. The sum of b squared and c squared times omega 1 squared, the sum of c squared and a squared times omega 2 squared, and the sum of a squared and b squared times omega 3 squared. If the width a, the length b and the height c are equal to each other, then the kinetic energy reduces to the expression stating that 1/12 times m times a squared, times the sum of omega 1 squared, omega 2 squared and omega 3 squared. Because the terms in the parentheses just give the square of the angular velocity omega, we obtain 1/12 times m times a squared times omega squared, which is the kinetic energy of a cube rotating about an axis passing through of its center. Now we discuss a special type of rotation about a fixed axis called torsional oscillation or torsional vibration, which is the oscillatory motion of a rigid body rotating about a vertical axis. Such a motion is produced by a body when it is slightly rotated about a vertical axis and released. For a given angular displacement of the body, torsional forces create a torque that tries to restore the equilibrium position of the body, causing it to rotate back and forth about the vertical axis. Torsion pendulums are mechanical devices used in laboratories to study torsional oscillations, and they basically have two different implementations. One type uses a torsion wire or a torsion fiber and the other one uses a spiral torsion spring. A torsion pendulum using a torsion wire or a torsion fiber consists of a mass suspended from the wire or fiber. Torsion wires are manufactured of stainless steel, whereas torsion fibers are made of silk, glass or quartz. The mass is normally a disc attached to the wire or the fiber at its center, on which a ring-shaped weight can also be mounted to increase the suspended mass as seen in the photo. If the disc is slightly rotated in the horizontal plane, a torque is generated due to the twist in the wire or fiber. As already mentioned, this torque is exerted on the disc by the twisted wire or fiber providing the restoring force acting on the disc. As a result, the disc will rotate back and forth about the vertical axis represented by the wire or fiber passing through its center of mass. A torsion pendulum utilizing a torsion spring has a more complex structure. A torsion spring is a spiral wound metal band that resists twisting or rotational motion, and it exerts a torque to return to its original position when twisted about the axle to which the spring is attached at the central axis of the spiral. If a stick is mounted horizontally on the top of the vertical axle, then some mass can be strung through the horizontal stick like beads as seen in the photo, and slightly rotated about the axle while twisting the spring. As a result, the torsion spring rotates back and forth as the spring untwists and twists, and it also rotates the vertical axle with the mass. We can determine the torque produced by the torsional forces in both types of pendulum if we measure the forces exerted by the vibrating disc or mass. This can be done by suspending weights from the oscillating disc to determine how much weight can compensate the torsional forces as seen in the figure, or attaching a dynamometer to the disc or mass rotated by the spring to measure the torsional forces directly, as seen in the photo. If we perform these experiments measuring the torsional force, we can demonstrate that the external torque required to rotate the pendulum from its equilibrium position through a small angle is proportional to the angular displacement. This is Hooke's law for torsion, and it states that the z component of the torque tau trying to restore the equilibrium position of a torsion pendulum rotated about its vertical axis pointing in the z direction through a small angle phi is given by minus a positive constant k times the angle phi, where k is the torsion coefficient of the pendulum. Its SI unit is Newton meter per radian, and it measures the change in torque required to twist a torsion pendulum through an angle of 1 radian. Hooke's law for torsion allows us to use this device for the direct measurement of torque after a calibration in a similar way as a calibrated coil spring is suitable for force measurement. Let us consider a body suspended from a torsion wire or properly attached to the vertical axle of a spiral torsion spring. If the moment of inertia of the wire or the spring denoted by I sub W/S is negligible compared to the moment of inertia I of the body with respect to the axis of the rotational oscillation, then the motion of the body produced by the torque can be determined from the law of conservation of angular momentum of the torsion pendulum applied for Hooke's law. As a result, we obtain the equation stating that the moment of inertia I of the body times the second-order derivative of the angular displacement phi of the body with respect to the time t is equal to minus the torsion coefficient k times the angular displacement phi. This equation can be written in the form where the second-order time derivative of phi is equal to the ratio of k over I times phi, where we define omega squared by the ratio of the torsion coefficient k to the moment of inertia I. Then we see that the equation of motion of the torsion pendulum has the same form as the one of the mathematical pendulum, that is, the motion of this device is a harmonic rotational vibration without damping. As already seen, the period t of harmonic oscillations is equal to 2 pi over omega, that is, the parameter omega is the angular frequency of the oscillation. In the case of the torsion pendulum vibrating about its vertical axis, the period is given by 2 pi times the square root of the ratio of the moment of inertia I of the rotating mass in the pendulum to the torsion coefficient k of the pendulum. This relationship allows us to determine the moment of inertia of the body by measuring the period in an experiment if the torsion coefficient of the pendulum is already known. We saw that the body is either a disc suspended from a torsion wire on which more weights can be placed, or some mass is strung through a horizontal stick mounted on the vertical axle of a torsional spring. In both the case, we can produce an arrangement where the axis of the torsional oscillation of the pendulum passes through the center of mass of these bodies. If we measure the period t of the oscillation of the mass, then we can express the moment of inertia I of the oscillation as the square of the torsion coefficient k over 4 pi squared, times the square of the period t. In the experiment we can measure the time of n periods and determine the period t as the measured time over the number n of the period. By repeating these measurements 3 times we can calculate the average of the results of the 3 measurements, which gives the final result used to determine the moment of inertia of the body performing torsional oscillations. The spiral spring and torsion pendulum are used in many measuring instruments, for example, in clocks, watches, microbalances, galvanometers, or in the different types of torsion pendulums constructed by Cavendish, Coulomb, and Utfusch. We already studied mathematical pendulums, which are only idealized models. In fact, pendulums always involve real objects approximated by rigid bodies, as also seen in the case of torsional pendulums. Hence, a physical pendulum is a rigid body that is free to rotate about a fixed horizontal axis under the influence of gravity. In fact, the axis of rotation does not need to be perfectly horizontal. If it has some inclination allowing the gravitational force to produce some torque rotating the body about the axis, then we can talk about a physical pendulum. A simple example of physical pendulums is a meter stick that can be suspended from a number of points, located at different distances from its center of mass, as seen in the photo where it is suspended at its end. If we pull it to one side from its equilibrium position and releases, then the meter stick will swing back and forth around a horizontal axis passing through the point of suspension, producing an oscillatory motion about its equilibrium position. Here we depicted a rigid body representing a physical pendulum, where the plane of the figure is the plane passing through the center of gravity C of the body that is perpendicular to the axis of rotation of the body at the point O of the suspension. The horizontal axis of rotation is chosen as the z-axis, and L denotes the length of the linear section between the points O and C. Applying the theorem of the center of mass, we can draw the vector representing the weight of the body given by its mass m times the gravitational acceleration g from the center of mass C of the body, where the line of action of this force is a vertical line passing through the point C. If the physical pendulum is pulled to one side from its stable equilibrium position and released, then it starts to swing back and forth. In the figure, the instantaneous angular displacement of the pendulum is described by the angle phi. The z component of the torque tau produced by the gravitational force is equal to the weight m times g, times the lever arm d, that is the perpendicular distance from the axis of rotation to the line of action of the weight. Because the lever arm d can be written as the length L times the sine of the angle phi of rotation of the body about the axis passing through of the point O, tau z is equal to minus m times g times L times sine phi. By substituting this result into the law of the conservation of angular momentum applied for the physical pendulum, we can write its equation of motion as follows. The moment of inertial I of the rigid body times the second-order derivative of the angular displacement phi with respect to the time t, is given by minus the mass m times the gravitational acceleration g times the length L, times sine phi. If we divide this equation by the moment of inertia I, then the equation of motion states that the second-order time derivative of the angular displacement phi of the pendulum is equal to minus the product of the mass m, the gravitational acceleration g, and the length L over the moment of inertial I, times the sine of the angle phi. Let us compare this equation with the equation of motion of the mathematical pendulum stating that the second-order time derivative of the angular displacement phi of the pendulum is equal to minus the ratio of the gravitational acceleration g to the length L of the pendulum, times the sine of the angle phi. If we introduce the notation Lr for the ratio of the moment of inertia I to the product of the mass m times the length L, then the equation of motion of a physical pendulum can be cast into the same form as the one obtained for the mathematical pendulum. Then we can state that the second-order time derivative of the angular displacement phi of the physical pendulum is equal to minus the gravitational acceleration g over Lr, times sine phi. This result shows that a physical pendulum swings with the same period as a mathematical pendulum of length Lr for small amplitudes of oscillation. The quantity 1 are given by the ratio of the moment of inertia of the body to the product of its mass, and the distance between the axis of rotation and the center of mass is called the reduced length of the physical pendulum. As in the case of the mathematical pendulum, the period t of the swings of a physical pendulum can be written as 2 pi times the square root of the ratio of the reduced length Lr to the gravitational acceleration g, or 2 pi times the square root of the ratio of the moment of inertia I to mass m times the gravitational acceleration g times the length L. For swinging with larger amplitudes, we can apply the same correction as the one already presented for a mathematical pendulum. If the reduced length Lr is measured from the point of rotation O along the line passing through the points O and C, then we obtain the point O' considered as the center of oscillation. This is the point at which the entire mass m of the physical pendulum could be concentrated without changing the period of oscillation of the pendulum. Now we present some examples and applications of physical pendulums. As the first example, we consider a thin homogeneous rod of length I that oscillates about an axis passing through its end point O and perpendicular to the rod. We already determined the momentum of inertia I of the rod about such an axis of rotation, and found that it is equal to the mass m of the rod times the square of the length L over 3. The reduced length Lr of the swinging rod is given by the ratio of its moment of inertia I to the product of the mass m of the rod and the length L sub OC of the linear section between the point O and the center of mass C of the rod. Because the later is just the half of the length L of the homogeneous rod, this ratio can be written as m times L squared divided by 3, over m times L divided by 2. As a result, the reduced length Lr of the rod is equal to 2 over 3, times the length L of the rod. The period of oscillation of the rod is therefore equal to the period the swinging of a mathematical pendulum of length Lr using a point like mass m as a bob. We can easily verify this by swinging the two pendulums side by side. The next example is a double pendulum with a common pivot that can be opened similarly to a compass, allowing the angle between the two pendulum rods of the same length to be fixed. If the bobs attached to the end of the pendulum rods have the same mass m, then the structure of such a double pendulum is symmetric about its equilibrium position. As a result, its center of mass C is always at the midpoint between the two bobs regardless of the opening angle of the pendulum rods. The period t1 of the pendulum is given by 2 pi times the square root of the ratio of its reduced length Lr to the gravitational acceleration g. Because the distance of the bobs from the pivot point O does not depend on the angle between the pendulum rods, the moment of inertia of the pendulum does not change with opening of the rods. However, the distance of the center of mass C from the point O can be modified by changing the angle between the pendulum rods, which also modifies the reduced length of the pendulum. For example, by opening the pendulum rods and increasing the angle alpha between them such that this distance is reduced by half, we can double the reduced length Lr of the pendulum, which increases its period by the factor of square root of 2. Hence the period of the pendulum can be modified by changing the angle alpha between the pendulum rods. The first application of physical pendulum shown here is the mechanical metronome, which is a device housed in a pyramid shape that produces a regular, repeated ticking sound serving as steady clicks to help musicians play in time. In metronomes, a wound-up spring drives a swinging pendulum with an adjustable sliding weight used to regulate the ticking sound. Below its pivot the pendulum consists of a weight attached to the pendulum bar, and above the pivot the smaller sliding weight can be moved along the bar. By moving the sliding weight higher along the bar, the height of center of mass of the pendulum can be decreased relative to the pivot, which also decreases the reduced length of the pendulum and at the same time increases its moment of inertia with respect to the pivot. These two effects cause a decrease in the period of the swing and the ticking sound produced by a clockwork mechanism connected with the pendulum bar. Another typical application of the physical pendulum is the pendulum clock, with the first specimen built by Huygens in 1656. In a pendulum clock, a pendulum controls the movement of a gear rotated by a weight that is wound up or by spiral spring with the help of an anchor properly connected to the swinging pendulum bar. The two tips of the anchor alternately reach between the teeth of the gear, and thus the gear rotates only one tooth further with each half of the swing, and the pendulum receives an impulse from the gear pointing in the direction of the instantaneous velocity of the gear. As a result of these periodic impulses, the swings of the pendulum are not damped, because the energy obtained from the impulses compensates the loss in the mechanical energy of the pendulum due to friction and air resistance. The next application of physical pendulums is the reversible pendulum seen in the photo. The idea of this kind of pendulum was first published by Johann G. F. Bonenberger in 1811, whereas the first reversible pendulum was constructed by Henry Kater in 1818, which is also called Kater's pendulum. As the schematic figure shows, the axis of rotation of the reversible pendulum perpendicular to the rod of the pendulum passes through the point O, and the distance of the point O' from the axis of rotation is given by the reduced length Lr of the pendulum. The pendulum consists of a metal bar with the two pivot points O and O', which are knife edges facing each other, and two weights attached to the two ends of the bar. This device has different types where either the pivot points or the weights are adjustable by sliding them up or down along the pendulum bar. Each of the sliding objects can be clamped in place on the bar. The pendulum can be suspended and set swinging by using either knife edge as a pivot, that is, the bar suspended from one of its pivot can be reversed and suspended from the other one. The operation of the reversible pendulum is based on the fact that the period of its oscillation does not change if its axis of rotation is replaced with a new axis parallel with the original one that passes through the point O'. In order to prove this statement, let us examine for which axes of rotation, that is, which suspension points O and O' provide the same period and the same reduced length in both the original and the reverse operation of an arbitrary physical pendulum. By applying the parallel axis theorem, we can write the moment of inertia I of the pendulum with respect to the pivot point O as the moment of inertia I c about the center of mass C of the pendulum, plus the product of its mass m and the square of the length measured between the points O and C. Since the reduced length Lr is equal to the moment of inertia I over the product of the mass m and the length L, we can express I from the theorem and insert the result into this ratio. Then the reduced length L is equal to the moment of inertia I c over m times L, plus L. This gives the quadratic equation stating that the square of the distance L minus the reduced length Lr times L, plus the moment of inertia I c over the mass m is equal to 0. If L1 and L2 are the roots of this quadratic equation, then the coefficient Lr of the term first order in L can be written as the sum of the two roots, that is, the reduced length is given by L1 plus L2. The pivot points O and O' therefore lie on two circles of radii L1 and L2 with the center at the center of mass C, and these circles intersect the line passing through the points O and C at four different points, namely at the points O and O' and at two other points denoted by Q and Q'. Of these, the point O is specifically at the distance Lr from the point O', where Lr is given by the sum of the radii L1 and L2. This result proves the statement about the equal periods. Accordingly, it is possible to achieve the same period of oscillation for the two axes of rotation of the reversible pendulum by adjusting either the pivot points or the weights. In such a case, the distance between the edges O and O' is equal to the reduced length Lr of the pendulum. By measuring the period and the reduced length with high accuracy, we can determine the gravitational acceleration g, which can be expressed by 4 pi squared times the ratio of the reduced length Lr to the square of the period t. The reversible pendulum thus provides a very accurate method for determining the acceleration of gravity at a particular location, and it is much more accurate than the mathematical pendulum, which is not perfectly feasible. If the value Ga of the gravitational acceleration is known at the place A on Earth, then it is enough to perform a relative measured at any other place B on Earth. By measuring the periods Ta and Tb at the locations A and B with the same reversible pendulum, we can determine the ratio of the acceleration of gravity Gb to the acceleration of gravity Ga by calculating the ratio of Ta squared to Tb squared. At the same time, we also see that in the measurements of the acceleration of gravity with reversible pendulums, the reduced length is given by the distance between the two axes of rotation, which are on both sides of the center of mass of the pendulum, and their locations are not symmetrical with respect to the center of mass c. While the distance between the points O and O' gives the reduced length of the pendulum, neither the distance between the points O and Q, nor the distance between the points O and Q' is equal to this length. Another interesting type of physical pendulums using knife edge as a pivot point is the balanced pendulum, which addresses the problem of blade wear as the rotating knife edges become blunt due to friction. Consequently, the distance is gradually reduced between the edge serving as its pivot point and the center of mass of the pendulum, also affecting the period of its oscillation. When designing pendulums used in precision clocks, the aim is to minimize the effect of the change in the distance between the pivot point and the center of mass of the pendulum on the reduced length of the pendulum, which determines its period. This condition is obviously fulfilled at a length L0 of the linear segment between the points O and C, for which the reduced length has an extremum, in this case a minimum, that is where the derivative of the reduced length Lr with respect to the length L vanishes. If we calculate the derivative of the expression obtained above for the reduced length, then this condition states that minus the moment of inertia c of the balanced pendulum about its center of mass over the product of its mass m and the square of the length L0, plus 1 is equal to 0. This equation can be solved for L0, and we can write the distance L0 minimizing the change in the reduced length as the square root of the ratio of the moment of inertia c to the mass m. Then we can express the moment of inertia c by the product of the mass m and the square of the length L0. By substituting this length into the moment of inertia in the equation of the reduced length, we see that Lr is given by L0 squared over L0 plus L0, which is equal to 2 times L0. That is, the length L0 minimizing the change in the period of the pendulum is the half of its reduced length. A pendulum that meets this condition, which can be for example a rod with weights at both ends, is called a balanced pendulum. The last example for a physical pendulum shown here is the horizontal pendulum, where the motion of the pendulum is horizontal or almost horizontal with some inclination. If the axis of rotation of the pendulum is not horizontal but makes an angle psi with the horizontal plane, then the torque produced by the gravitational force will rotate the pendulum about the axis. As already seen, the force acting on a vertical pendulum in the direction tangential to its trajectory is equal to its mass m times the gravitational acceleration g times the sine of the angle of rotation phi. In the case of a horizontal pendulum, this component of the force need to be projected onto the plane of the motion of the pendulum, and this value must therefore be multiplied by the cosine of the inclination angle psi of the plane. As a result, the torque of the gravitational force is equal to minus the mass m, times the acceleration of gravity g, times the length L of the pendulum, times the sine of the rotation angle phi of the pendulum, times the cosine of the inclination angle psi of the plane of the oscillation. Accordingly, the period t of the oscillation is given by 2 pi times the square root of the ratio of the reduced length Lr to the product of the gravitational acceleration g and cosine psi. This formula shows that in the case of a nearly vertical axis of rotation, where psi is almost equal to the right angle like in the case of a door, the period is very large. Such a horizontal pendulum swinging in a nearly horizontal plane is used in layman seismographs for observation and registration of earthquakes, since its equilibrium position and oscillation period are very sensitive to changes in the position of the axis of rotation. Now we discuss the motion of bodies rolling down an inclined plane. If a ball is released on a slope of inclination angle alpha with zero initial velocity, we find that the center of mass of the rolling ball performs a uniformly accelerating motion. We already saw that the distance s covered by a uniformly accelerating body during the time t is equal to its acceleration a times the square of the time t over 2. However, the acceleration a of the ball is considerably less than the component of the acceleration of gravity tangent to the slope given by the gravitational acceleration g times the sine of the inclination angle alpha. We can also perform another experiment where a solid wooden cylinder and a hollow metal cylinder of the same mass, radius and length are placed next to each other on the slope. Of the two cylinders released at the same time, the hollow cylinder rolls down the inclined plane slower than the solid cylinder, since its moment of inertia about the axis of symmetry is greater than that of the solid cylinder. Let us analyze these results quantitatively. At a given instant of time, the line of contact between a rolling cylinder and the surface of the slope is the instantaneous axis of rotation of the cylinder. Similarly, the line passing through the point of contact P between a rolling sphere and the surface of the slope such that the line is perpendicular to the direction of the motion of the center of mass C of the sphere, is also the instantaneous axis of rotation of the sphere. If a body rolling down an incline rotates about this axis through a small angle delta phi, then its center of mass C will cover the small distance delta s given by the radius r of the cylinder or the sphere times the angular displacement delta phi of the point C. The equation of motion of the body rotating about the instantaneous axis of rotation states that the moment of inertia ip of the body with respect to the instantaneous axis of rotation determined by the point P, times the second-order time derivative of the angular displacement phi of the body is equal to the z component of the torque tau produced by the gravitational force acting on the body, where the axis of rotation is chosen as the z-axis. The z component of the torque tau is equal to the weight of the body given by its mass m times the gravitational acceleration g, times the lever arm d of the weight pointing downward from the center of mass c. Here the lever arm can be written as the radius r times the sine of the inclination angle alpha of the slope. Because the infinitesimal displacement ds of the center of mass c of the body is equal to the radius r times the infinitesimal rotation angle d phi of the body, we can express the second-order time derivative of the angle phi by 1 over r, times the second-order time derivative of the displacement s. By applying the definition of acceleration, we can write the second-order time derivative of the angular displacement as the acceleration a of the center of mass c over the radius r. As a result, the equation of motion states that the moment of inertial ip times the acceleration a over the radius r, is equal to the mass m times the acceleration of gravity g times the radius r, times sine alpha. If we express the acceleration a of the center of mass c from this equation, then we obtain the ratio of the mass m times the square of the radius r to the moment of inertia ip, times sine alpha. Now we can apply the parallel axis theorem stating that the moment of inertia ip of the body about its instantaneous axis of rotation passing through the point of contact P, is equal to the moment of inertia ic of the body with respect to the parallel axis passing through the center of mass c, plus the product of its mass m and the square of its radius r. Then the acceleration a of the center of mass of a cylinder or a sphere of mass m and radius r rolling down a slope with the inclination angle alpha, is given by the ratio of the mass m times the square of the radius r to the sum of m times r squared and the moment of inertia ic, times the gravitational acceleration g times sine alpha. We already saw that the moment of inertia ic is given by 2 over 5 times the mass m times the square of the radius r in the case of a sphere with uniform density. By inserting this expression into the formula obtained for the acceleration, we can write it as 5 over 7 times the acceleration of gravity g times sine alpha for a homogeneous sphere rolling down a slope with the inclination angle alpha. Similarly, since the moment of inertia ic of a homogeneous cylinder is equal to 1 over 2 times its mass m times the square of its radius r, its acceleration on the incline is given by 2 over 3 times the gravitational acceleration g times sine alpha. We also saw that the moment of inertia ic of a hollow cylinder is equal to 1 over 2 times its mass m, times the sum of the square of its inner radius ri and the square of its outer radius r. If the wall of the hollow cylinder is thin, then the inner radius can be approximated by the outer one, which gives m times r squared for the moment of inertia. In this case, the acceleration a of the hollow cylinder while rolling down the slope is approximately equal to 1 over 2 times the gravitational acceleration g, times the sine of the inclination angle alpha of the slope. The qualitative explanation of these findings are the following. The torque exerted on a cylinder and a hollow cylinder is the same, but it will produce a smaller angular acceleration for a hollow cylinder due to its greater moment of inertia about its axis of rotation. Consequently, a hollow cylinder will roll down an incline slower than a cylinder of the same mass and radius. Now we determine the kinetic energy of a sphere rolling down an inclined plane and examine the forces accelerating the body. In the case of this type of motion, the kinetic energy of the homogeneous body of mass m consists of two parts. The first part is the energy of a point mass m concentrated in the center of the mass c of the body, where the point mass travels with the velocity v having the kinetic energy 1/2 times the mass m times the square of the velocity v. The second part gives the energy of the body rotating about its central axis, which is equal to 1/2 times the moment of inertia I of the body with respect to its central axis, times the square of its angular velocity omega. If the body rolls down the slope without sliding, then its angular velocity omega can be written as the ratio of the velocity v to the radius r of the sphere or cylinder. By substituting this expression into the second term, we are able to express the kinetic energy of a sphere of a cylinder of mass m and radius r rolling down an incline as 1/2 times the mass m, times the square of the velocity v of its center of mass, times the quantity of 1 plus the moment of inertia I of the body over the product of the mass m and the square of the radius r. Because the moment of inertia I c of the sphere with respect to its central axis is equal to 2/5 times its mass m times the square of its radius r, the kinetic energy of the rolling sphere can be written as 7/10 times m times v squared. Similarly, for a rolling cylinder with the moment of inertia I c given by 1/2 times its mass m times the square of its radius r, the kinetic energy is equal to 3/4 times m times v squared. This expression can be compared with the kinetic energy of a rolling hollow cylinder with the moment of inertia I c approximated by its mass m times the square of its radius r, which is simply equal to m times v squared. The result shows that the hollow cylinder has a greater kinetic energy than the solid cylinder of the same mass and radius if their centers of mass have the same instantaneous velocity. Now we study the forces exerted on a homogeneous sphere of mass m rolling down a slope with the inclination angle alpha. The weight of the sphere given by its mass m times the acceleration of gravity g can be decomposed into the vector sum of the tangential force Ft and the normal component Fn of the weight, pointing into the direction tangent and perpendicular to the motion of the center of mass c of the sphere. Here the magnitude of the tangential component is equal to the mass m times the gravitational acceleration g, times the sine of the inclination angle alpha of the slope, whereas the magnitude of the normal component is equal to m times g times cosine alpha. Due to the law of action and reaction, the slope exerts the force minus Fn on the sphere compensating the force Fn. We also have to take the static frictional force F sub Tf into account, acting in the direction opposite to the tangential force Ft at the point of contact P. We already proved that a system of forces can be replaced by one force applied at an arbitrary point and a force couple producing a given torque with respect to that point. Then the tangential force Ft and the frictional force F sub Tf are equivalent to their net force F sub T1 applied at the center of mass c in the tangential direction, and the force couple F sub T2 and F sub Tf that produces the torque rotating the sphere about the point c. Consequently, the magnitude of the force F sub T1 is equal to the magnitude of the tangential force Ft minus the magnitude of the frictional force F sub Tf, and this net force will produce the acceleration a of the center of mass of the sphere of mass m. As already seen, the acceleration a of a sphere of mass m rolling down a slope with the inclination angle alpha is given by 5/7 times the mass m times the gravitational acceleration g, times sine alpha, which we substitute into the right-hand side of the equation. By applying the explicit form of the tangential component of the force, we can express the frictional force F sub Tf by 2/7 times m times g times sine alpha. The angular acceleration of the sphere about its central axis is due to the torque tau produced by the frictional force F sub Tf, and its magnitude is given by the magnitude of the force F sub Tf times the radius r of the sphere, which is equal to 2/7 times the mass m times the acceleration of gravity g times sine alpha, times the radius r. After the presentation on bodies rolling down an incline, we discuss rolling friction or rolling resistance that slows down the motion of a rolling object. We saw that the acceleration a of a sphere rolling down a slope is given by 2/5 times the acceleration of gravity g times the sine of the inclination angle alpha of the slope. If a ball is rolling across the horizontal surface of a table, the inclination angle is 0 and the rolling body has no acceleration. Then we would expect that the ball performs a uniform rectilinear motion across the table and it will never stop rolling over an infinite horizontal surface. But experience shows that the rolling ball slows down and stops after covering a finite distance, due to friction and drag effects. Now we provide the quantitative description of this effect. Because of the deformation of the bodies in contact that always occurs in reality, the ball does not come into contact with the plane at one point but over a surface. The table exerts forces on the ball over the surface of contact that are greater at the point A than the forces at the point B for the direction of the rolling ball shown in the figure. As a result, the forces exerted on the ball produce a torque in the opposite direction of the rotation of the ball, reducing the angular velocity of the rotation and the velocity of the center of mass of the ball. Experience also shows that the magnitude of the torque tau with respect to the instantaneous axis of rotation of the ball is approximately proportional to the force N that presses the body against the surface. The proportionality constant denoted by the letter B is known as the coefficient of rolling friction that depends on materials and geometry. The dimension of this coefficient is length and its SI unit is meter, although millimeter is more frequently used in practice. Alternatively, the rolling resistance can also be described by the equation stating that the frictional force F sub F is directly proportional to the normal force N, where the dimensionless constant of proportionality μ is called the coefficient of rolling friction as well. The relation between the dimensionless coefficient and the one with the dimension of length can be derived from the expression stating that the magnitude of the torque tau is equal to the frictional force F sub F, times the lever arm given by the radius r of the rolling ball or sphere. If we substitute the equations expressing the torque and the frictional force in terms of the two types of coefficients of friction into this equation, we can write that the coefficient of rolling friction B as the product of the radius r and the dimensionless coefficient of rolling friction μr. Equivalently, the dimensionless coefficient of rolling friction μr is equal to the ratio of the coefficient of rolling friction B to the radius r. We can find measured data for both types of coefficients in the literature, but it might be more convenient to use the dimensionless coefficient since it does not involve any length scale. In this table we show the dimensionless coefficient of rolling friction μr for some typical cases from everyday life, starting with a rolling resistance for railroad steel wheels on steel rails, which has a very low value between 0.001 and 0.002. These figures are also the same for ball bearings. The rolling friction for bicycle tires rolling on concrete is equal to 0.002, whereas it goes up to 0.004 in the case of an asphalt road. This coefficient is already one order of magnitude greater for car tires. It is equal to 0.02 when the car is traveling on asphalt, and it increases to 0.2 or 0.4 for car tires rolling on loose sand. There are several methods to measure the coefficient of rolling friction by conducting experiments with bodies made of different materials rolling across different surfaces. For example, the coefficient of rolling friction can be determined by finding the angle of inclination alpha naught of a ramp at which a ball or sphere rolls down with a uniform velocity after a small push. The torque tau produced by the weight of the body with respect to its instantaneous axis of rotation is equal to the mass m of the body times the gravitational acceleration g, times the radius r of the body, times the sine of the angle alpha naught. The torque produced by friction is given by the product of the coefficient of rolling friction B and the magnitude of the normal force N pushing the ball against the ramp, where N can be written as the mass m times the gravitational acceleration g, times the cosine of the angle alpha naught. If the motion of the center of mass of the rolling body is uniform, the magnitude of the torque due to rolling friction must be equal to the magnitude of the torque tau. As a result, we can write that m times g times r times sine alpha naught is equal to b times m times g, times cosine alpha naught. By simplifying this equation, we can express the coefficient of rolling friction B as the radius r of the rolling body, times the tangent of the inclination angle alpha naught of the slope on which the body rolls down with a uniform velocity. Then the tangent of the angle of inclination alpha naught immediately gives the dimensionless coefficient of rolling friction μ of the ball rolling down the ramp. For a wheel of radius r rolling on the ground with a constant speed, the torque tau produced by the pulling force Fp acting in the heel hub is equal to the force Fp times the lever arm given by the radius r. Because this torque is equal to the one due to rolling friction given by the coefficient of rolling friction B times the normal force N, the force Fp can be expressed by B times the ratio of N to r, or the coefficient of rolling friction μ times the normal force N. This formula shows that the force required to drive the wheel is inversely proportional to the radius of the wheel. That is, larger wheels will generally roll over object easier than smaller ones. By applying these results, we can compare the forces that will be required to pull a car or a sledge of the same weight across asphalt. We saw that the coefficient of rolling friction μ is equal to about 0.02 for car tires in such a case. The coefficient of sliding friction μ for a sledge on dry asphalt is generally in the range of 0.7 to 0.8. Here we have the equations for the forces required to pull a car or a sledge stating that they are equal to the coefficient of rolling friction μ times the normal force given by the weight g of the car, and the coefficient of sliding friction μ times the normal force given by the weight g of the sledge. If we divide the first equation by the second one, we can write that the ratio of the force applied on the car to the force applied on the sledge is equal to the ratio of the coefficient of rolling friction μ to the coefficient of sliding friction μ. After having substituted the values 0.02 and 0.8 into the fraction, we obtain 1/40, that is, on dry asphalt a car can be pulled by 40 times less force than a sledge of the same weight. In a car, the engine provides the torque tau necessary for smooth rolling, which corresponds to a force F acting backward at the point of contact between the wheels and the road. The magnitude of this force is given by the magnitude of the torque tau over the radius r of the wheels of the car. The reaction to this force is the sticking frictional force Fs pointing forward, which is an external force driving the car forward, provided the force F is smaller than the threshold value of the sticking frictional force Fs. Otherwise, the wheels will slide instead of rolling when the force F is applied on them. This condition can be formulated by the inequality stating that the driving force F given by the ratio of the torque tau to the radius r of the wheel must be less than the maximum of the sticking frictional force Fs, where the later is equal to the coefficient of sticking friction μs times the weight g' exerted on each wheel. This inequality can also be applied for any other vehicle using wheels, such as bikes, trams or trains. In order to fulfill this condition imposed on the force F, we need a vehicle that has large weight and an engine that produces much power. We already studied rigid rotation, that is the rotation of a rigid body about a fixed axis. Now we will discuss another type of rotation of objects where the axis of rotation is not fixed but free. As everyday experience shows, a rigid body that is not subjected to external forces or the net external force acting on it vanishes can revolve around certain non-fixed axes while the orientation of the axis of rotation does not change. Such axes are the so-called free axes of rotation, and when bodies rotate about, then we can talk about free rotation. For example, a coin, a plate, or a flat disk can be made to rotate permanently around its diameter as an axis. Skillful acrobats are also able to balance and spin plates or disks on the tip of a stick about the axis of symmetry of the plate. The vertical direction of free axes can be studied experimentally by suspending the body with different orientations from the vertical axle of the rotating motor. For example, we can demonstrate in the experiment that a flat cylinder in vertical position can rotate sustainably around the transverse axis A1 passing through its center of mass and the point of its suspension, that is, the axis A1 is a free axis. For a faster rotation, the instabilities occurring in the process cause for the disk to flip to a horizontal position and spin about its vertical axis of symmetry A2, that is, the axis A2 is also a free axis of rotation. For any perturbation causing a deviation of the disk rotating about the axis A2 from its horizontal position, the spinning disk will return to its horizontal position, which shows that the stability of the rotation about the symmetry axis of A2 as a free axis is greater than that of the rotation about the axis A1. The case of a tall cylinder is the opposite, where the rotation around the transverse axis A1 appears to be more stable. In the study of the moment of inertia in rigid rotation, we already saw that the axes A1 and A2 determined in this experiment are the principal axes of inertia of both the cylinders with respect to these axes passing through their centers of mass. The moment of inertia of the flat cylinder with respect to the axis of symmetry A1 is the greatest of the moments of inertia about all the central axes of a cylinder. Similarly, the moment of inertia of the tall cylinder with respect to the transverse axis A2 is the greatest of the moments of inertia about all the central axes of a cylinder. Hence, in both cases the free axis with the greatest stability is the one with the largest moment of inertia. When we studied the moment of inertia of rigid bodies about their axes of symmetry, we presented their formulae computed for different solids. We saw that the moment of inertia I1 of a cylinder with uniform density about the axis A1 is equal to 1/4 times the mass m of the cylinder times the square of its radius r, plus 1/12 times the mass m times the square of the height h of the cylinder. Similarly, the moment inertia I2 of a cylinder with respect to the axis A2 is given by 1/2 times the mass m of the cylinder times the square of its radius r. The rotation of a cylinder about the axes A1 and A2 has the same stability for the condition stating that the moments of inertia I1 and I2 are the same. If we substitute the expressions obtained for I1 and I2 into this condition, then we can write the equation stating that 1/12 times m times h squared is equal to 1/4 times m times r squared. This gives the relation stating that 1/3 times h squared is equal to r squared, and we conclude that if the height h of a cylinder is equal to the square root of 3 times its radius r, then its rotation will be stable about both the central axes A1 and A2. We can also apply this condition to identify a cylinder of uniform density as a flat cylinder or a long one, depending whether its height h is greater or less than the square root of 3 times its radius r. Experiments with a homogeneous rectangular body lead to similar results. We already determined the moment of inertia of a cuboid with length a, width b and height c with respect to its principal axes A, B and C passing through the center of mass of the body, where these axes are the axes of symmetry of the cuboid. The moment of inertia Ia with respect to the axis A is equal to 1 over 12 times the mass m of the cuboid, times the sum of b squared and c squared. Obviously the terms in the sum in the expression of the moment of inertia Ib with respect to the axis B are a squared and c squared, and the terms in the sum in the expression of the moment of inertia Ic with respect to the axis C are a squared and b squared. These formulae show that if the length is a is greater than the width b and the width b is greater than the height c, then the moment of inertia Ic is greater than the moment of inertia Ib, and the later is greater than the moment of inertia Ia. It can be demonstrated in the experiments with a cuboid rotating about the principal axes that the central axes A and C are free axes, and the rotation about the axis C with the largest moment of inertia Ic is more stable. On closer inspection, the axis B is also a free axis, but the rotation about it is unstable, that is, its realization is as difficult as, for example, setting a cone to the apex. The above can be ascertained in a simple experiment with a box of matches thrown in the air by spinning it properly. The flying box can rotate permanently about the axes A or C, but not about the axis B. Based on our knowledge on the rotation of objects about fixed axes, we can determine the laws related to free axes. If a rigid body of arbitrary shape and mass distribution rotates with a constant angular velocity omega about an axle supported by ball bearings fixing its vertical direction along the z-axis, then all the mass elements mi of the body are subjected to the centripetal force Fi'. This force is the external constraint force exerted on the mass elements by the ball bearings, and it is equal to minus the mass mi times the square of the angular velocity omega, times the distance vector di of the mass element mi pointing from the axis of rotation to the mass element. When we studied systems of forces applied on rigid bodies, we proved that these systems can be reduced to the net force of the system acting on the body and a force couple producing a given torque on the body. According to this theorem on the reduction of a system of forces, the constraint forces Fi' acting on the mass elements of the body can be combined into or replaced by a net force F' applied on the body and a force couple producing a torque τ' rotating the body. If both the net force F' and the torque τ' vanish, that is, if the ball bearings do not exert either force or torque on the body or on the axis of rotation relative to the body, then the ball bearings can be removed, and the axis of rotation of the rigid body is a free axis. Let us discuss the consequences of the vanishing net force acting on a rotating rigid body and the vanishing torque produced by the forces that the ball bearings exert on the axle about which the body is rotating. If dc denotes the direction vector pointing from the axis of rotation to the center of mass c of the rigid body, then the acceleration a of the center of mass rotating with the angular velocity omega is equal to minus the square of the angular velocity omega, times the distance vector dc. The theorem for the motion of center of mass of mechanical systems tells us that the center of mass of a rigid body moves as if the total mass of the system were concentrated at the center of mass, and the net force of all the external forces acting on the system were applied there. Consequently, the net force F' acting on the body given by the mass m of the body times the acceleration a, is equal to minus the mass m times the square of the angular velocity omega, times the distance vector dc. If the net force F' exerted on the system rotating about a free axis vanishes, then the length of the distance vector dc must be equal to 0, that is, the center of mass of the rigid body must be on the free axis of rotation. We can also examine the consequences of the vanishing net torque produced by the force couple arising from the reduction of forces applied on the body. Let us suppose that the center of mass c of the body is on the z-axis, that is on the axis of rotation, and determine the net torque τ' of the torques τ' I produced by the forces F' I acting on the volume elements mi of the body with respect to the center of mass. The net torque τ' can be written as the sum of the cross product of the position vector Ri pointing from the center of mass c to the mass element mi, and the force Fi' exerted on the mass element from I equals 1 to the number of the mass elements n in the rigid body. As already seen, the force Fi' is equal to minus mi times omega squared times di, and the net torque is given by minus the square of the angular velocity omega, times the sum of the mass mi times the cross product of the position vector Ri and the distance vector di from I equals 1 to n. Let xi, yi and zi be the coordinates of the position vector Ri in the Cartesian coordinate system attached to the rotating body, that is where the coordinate system rotates with the angular velocity omega about the z-axis. In the case of the horizontal distance vector di pointing from the z-axis to the mass element mi, the z-coordinate vanishes for any mass element. Then we can write the components of the torque τ' as follows. Its x component is equal to omega squared times the sum of mi times yi times zi from I equals 1 to n, its y component is given by minus omega squared times the sum of mi times zi times xi from I equals 1 to n, and the z component vanishes. As a result, for the vanishing net torque tau prime, the products of inertia of the body with respect to the z-axis must be equal to 0, that is both I sub yz given by the sum of mi times yi times zi from I equals 1 to n, and I sub xz given by the sum of mi times zi times xi from I equals 1 to n must vanish. When we studied the moments and products of inertia of a body in the principal axis system, we saw that the products of inertia of a rotating body vanish in the principal axis system of the body. That is, the condition of vanishing net torque holds if the z-axis of rotation is one of the principal axis of the body, which passes through the center of mass c of the body. It follows from these considerations and the law of action and reaction that a rigid body rotating about an axle chosen as the fixed z-axis with an angular velocity omega exerts the force minus F prime and the torque minus tau prime on the structure fixing the direction of the axle. Here minus F prime is given by the mass m of the body times the angular velocity omega, times the distance vector dc pointing from the z-axis to the center of mass c of the body. Similarly, minus tau prime is equal to omega squared, times the sum of the mass mi times the cross product of the position vector ri of the mass element with respect to the center of mass c on the z-axis, and the distance vector di of the mass element pointing from the z-axis to the mass element. The directions of the net force and torque are constant with respect to the body, that is, they rotate with the body. In the case of fast rotation, the magnitudes of the force F prime and the torque tau prime can be very large if the center of mass is not exactly on the axis of rotation, or if the products of inertia I sub yz and I sub zx do not vanish. The results derived from the experiments or deduced from the conditions of the vanishing net force and torque can be summarized as follows. A rigid body generally has three mutually perpendicular free axes, namely the three principal axes of inertia passing through the center of mass of the body, which was showed by Johann Andreas Segner, a German physicist in 1755, and applied by the Swiss polymath Leonhard Euler between 1758 and 1765 to derive his equations describing the rotation of rigid bodies. With regard to the instability of the free axes, we have found that the rotation is stable about the axes corresponding to the largest and the smallest moment of inertia of the body, whereas the rotation is unstable is about the third principal axis for which the moment of inertia has the middle value. The most stable axis for free rotation is the one with the largest moment of inertia. As already stated, the principal axes A, B, and C of a rotating body with respect to the axis of rotation determined by the angles alpha, beta, and gamma passing through the point O, are aligned with the axes of symmetry of the ellipsoid of inertia of the body with respect to the point O. In the special case, where the ellipsoid of inertia of a body with respect to its center of mass is a rotational ellipsoid, that is, for example, IA is equal to IB but they are not equal to IC, as in the case of a homogeneous cylinder, all other central axes of the body lying in the plane of the principal axes A and B are also free axes. If all the principal moments of inertia of the body are the same, as in the case of a homogeneous sphere or cube, then all the central axes of the body are free axes of rotation. We can also talk about free axes in the case of the rotation of non-rigid bodies. For example, in a somersault the transverse axis passing through the center of gravity of the jumper's body is a free axis, whereas the free axis of a spinning skater is the longitudinal axis of the skater's body. The jumper and the skater can significantly change their moments of inertia with respect to the free axis during rotation, so that the angular velocity of their rotation also changes according to the conservation of their angular momentum, stating that the product of the moment of inertia and the angular velocity of the bodies of the jumper and skater must be constant. In physics, a rigid body of arbitrary shape and mass distribution is called a spinning top or simply a top, if it rotates either about a fixed point of the body or any of its non-fixed point that does not change its position during the rotation. For example, the motion of a flying disc or the front wheel of a bicycle about its center of mass can often be ignored in the first approximation, and the disc or the wheel rotating about its center of mass supposed to be at rest can also be considered as a spinning top. We already saw that the lengths A, B, and C measured along the symmetry axes of the inertia ellipsoid of a rigid body with respect to the instantaneous axis of rotation passing through the point O given by the angles alpha, beta, and gamma, determine the principal moments of inertia IA, IB, and IC of the body with respect to the axis of rotation. The principal moments of inertia of the body with respect to the point O of rotation are generally not the same, and the motion of the body can be very complicated. Therefore, we will only deal with the symmetric top, perhaps the most frequently used spinning top in practice, for which two of the three principal moments of inertia of the body are equal to each other, and the center of mass of the body is on the axis of symmetry. Consequently, the ellipsoid of inertia for a symmetric top with respect to the point O of rotation is a rotational ellipsoid. For example, a homogeneous cylinder or other solid of revolution like the spinning top shown in the first photo is a symmetric top, if the fixed point O is a point on the axis of symmetry of the body. Flat tops also occur in many applications. Their moment of inertia is the largest for the axis of symmetry, that is, the principal moment of inertia IC is greater than the principal moment of inertia IA, while in the case of elongated tops IC is less than IA. Spherical tops are normally considered as a class separated from symmetric tops, but they can also be regarded as a special case of symmetric tops, where all three principal moments of inertia are equal. In the case of a force-free top or torque-free top, the net torque with respect to the point O that is produced by the external forces acting on the body is equal to zero. In order for the gravitational force not to exert a torque on the top, the point O must coincide with the center of mass C of the body. This can be accomplished, for example, by properly adjusting the weight that can be shifted on the rod of the spinning top, or by using the cardan suspension or gimbal system, where a set of two or more pivoting rings called gimbals with intersecting axes allow an inner object to remain level or keep its orientation regardless of the motion and the instantaneous orientation of the outer support. In order to study the motion of a force-free top, let us determine the angular momentum of a spinning top. We already saw that the angular momentum L of a rigid body can be determined by approximating the body with a system of point masses mi, and it can be written as the sum of the cross product of the position vector Ri of the mass element mi with respect to a point O on the axis of rotation, and the momentum pi of the point mass from I equals 1 to the number n of the point masses. The momentum pi of the point mass mi is equal to the mass mi times the velocity vi of the point mass mi, where the velocity vi of the rotating point mass can be written as the cross product of the angular velocity vector omega of the rotating rigid body, and the position vector Ri of the point mass. Because the sum in the right-hand side has the triple cross product of the vectors Ri, omega and Ri, we can apply the vector identity stating that the cross product of the vector A with the cross product of the vectors B and C is equal to the dot product of A and C times B minus the dot product of A and B times C. Then the angular momentum L of the spinning top is given by the sum of the mass mi times the difference between the dot product of Ri with itself, times omega, and the dot product of Ri and omega, times Ri, from I equals 1 to n. As a result, we obtain the sum of mi times Ri squared times the vector omega from I equals 1 to n, minus the sum of mi times the dot product of Ri and omega times the vector Ri, from I equals 1 to n. Now we determine the components of the angular momentum L of the rotating body in a Cartesian coordinate system with the origin O, where the coordinates of the position vector Ri are given by xi, yi and zi. The x component of the angular momentum L is equal to the sum of mi times Ri squared times the x component of the vector omega from I equals 1 to n, minus the sum of mi times the quantity of xi times omega x, plus yi times omega y, plus zi times omega z, times xi, from I equals 1 to n. If we gather the terms containing omega x, then we can write the right-hand side as the sum of mi times the difference between Ri squared and xi squared times omega x from I equals 1 to n, minus the sum of mi times the quantity of xi times yi times omega y, plus xi times zi times omega z from I equals 1 to n. By expressing the square of the position vector Ri in the terms of coordinates, we can write the first term as the sum of the mass mi times the square of the y-coordinate of the position vector Ri plus the square of its z-coordinate, times the x-coordinate of the angular velocity vector omega from I equals 1 to n. The second term in the right-hand side then is expressed as minus the sum of the mass mi times the product of the x and y coordinates of the position vector Ri, times the y-coordinate of the angular velocity vector omega from I equals 1 to n. Finally, the third term in the right-hand side is given by minus the sum of the mass mi times the product of the x and z coordinates of the position vector Ri, times the z coordinate of the angular velocity vector omega from I equals 1 to n. If we look at these three terms in the result, we can identify the moment of inertia I sub xx of the body in the first term, the product of inertia I sub xy in the second term, and the product of inertia I sub xz in the third term. Then we state that the x component of the angular momentum L of the spinning top is given by the product of the moment of inertia I sub xx and the x component of the angular velocity omega, plus the product of inertia I sub xy times the y component of the angular velocity omega, plus the product of inertia I sub xz times the z component of the angular velocity omega. This is the general expression for the x-coordinate of the angular momentum vector L of a spinning top written in a Cartesian coordinate system that is not a principal axis system of the rotating body. Obviously, we obtain the same result if we expand the triple cross product of the vectors Ri, omega and Ri in the coordinate system instead of using the vector identity. The cross product of omega and Ri gives a vector with the components zi times omega y minus yi times omega z, xi times omega z minus zi times omega x, and yi times omega x minus xi times omega y. Then the x component of the triple product given by yi times the z component of the cross product of omega and Ri, minus zi times the y component of the cross product of omega and Ri, can be written as follows. Yi times the difference between yi times omega x and xi times omega y, minus zi times the difference between xi times omega z and zi times omega x. By reordering the terms in the right-hand side we will have the sum of yi squared and zi squared times omega x, minus yi times xi times omega y, minus zi times xi times omega z. If we insert this result in the triple product in the expression of the x component of the angular momentum L, we obtain the same result as the one derived by applying the vector identity. We can repeat the same calculations to derive the y and z components of the angular momentum of a rotating body in a Cartesian coordinate system with the origin at the axis of rotation. Then besides the x component of the L vector, we obtain its y component given by the product of inertia I sub yx times the x component of omega, plus the moment of inertia I sub yy times the y component of omega, plus the product of inertia I sub yz times the z component of omega. Similarly, the z component of the angular momentum L can be written as the product of inertia I sub zx times the x component of omega, plus the product of inertia I sub zy times the y component of omega, plus the moment of inertia I sub zz times the z component of omega. Here we also show all the moments and products of inertia of the body approximated by a system of point masses with respect to the axis of rotation passing through the origin of the coordinate system. By inspecting the structure of the three-component equations of the angular momentum L, we can introduce a matrix notation for the complete set of moments and products of inertia of a rigid body with respect to a point or an axis of rotation. The moment of inertia matrix I with the diagonal elements given by the moments of inertia and the off-diagonal elements given by the products of inertia is a symmetric matrix, as the explicit forms of the matrix elements show, which are constructed from the quadratic sums and the products of the Cartesian coordinates of the point masses approximating the rigid body. Consequently, we can state that the angular momentum L of a rigid body rotating with a given angular velocity omega about a given axis described by the angular velocity vector omega is equal to the product of the moment of inertia matrix I of the rigid body and the angular velocity vector omega. Since the vectors and the matrix in this vector equation are physical quantities, the choice of the coordinate system in which the vector components and the matrix elements are expanded has no role in determining the angular momentum vector from the moment of inertia matrix and the angular velocity vector. Similar to the invariance properties of the dot and cross products of vectors with respect to coordinate transformations, it can be shown that the product of the moment of inertia matrix and the angular velocity vector transforms as a vector under coordinate transformations. If we select another coordinate system and determine the elements of the moment of inertia matrix I and the components of the angular velocity vector omega in the new coordinate system, then the components of the angular momentum L in the new coordinate system are given by the matrix vector product expanded in the new coordinate system. This indicates that the collection of the moments and products of inertia of a rigid body with respect to a given axis of rotation can be interpreted as a linear map on the Euclidean space. That is, the map I defined for a rigid body rotating about a given axis transforms the angular velocity vector omega describing the speed of rotation and the orientation of the axis into the vector of the angular momentum L of the rotating body with respect to the axis. The evaluation of the linear map I at the vector omega is simply defined by the matrix vector multiplication of the matrix I and the vector omega expanded in an arbitrary coordinate system. This linear map is a second-order symmetric tensor called the moment of inertia tensor of a rigid body with respect to an axis of rotation, and the matrix is just the representation of the tensor in a given coordinate system. A different choice of a coordinate system provides a different representation of the moment of inertia tensor of a rigid body with respect to a given axis of rotation. Based on these concepts, the rotational energy, or the kinetic energy of a rotating rigid body with a center of mass at rest can be expressed in the terms of the moment of inertia tensor and the angular velocity vector of the body. We already saw that the sum of the products of the principal moments of inertia of a rigid body rotating about a fixed axis and the square of the components of the angular velocity vector describing the rotation determines the kinetic energy of the body in a principal axis system. We can generalize this result by expressing the kinetic energy of a rotating body by 1/2 times the dot product of the angular momentum L of the body and the angular velocity vector omega. If we substitute the product of the moment of inertia matrix I and the angular velocity vector omega into the angular momentum L, we can write the kinetic energy as 1/2 times the dot product of omega and the product of I and omega. Because the dot product is associated with the matrix vector product, we do not need parentheses in this expression. Hence the kinetic energy is equal to 1/2 times the symmetric quadratic form I of the moment of inertia of the body evaluated at the angular velocity vector omega of the body. That is, the second-order symmetric tensor I maps the Cartesian products of two three-dimensional Euclidean spaces onto the real line, where the mapping of the Cartesian product of the vector omega with itself is defined by the vector omega times the matrix I times the vector omega. We note that tensors are important mathematical objects applied in physics to describe physical quantities. In the beginning of this course we introduced scalars representing a fundamental mathematical description of physical quantities which are determined by one real number and a unit, for example the mass of point-like objects or rigid bodies. In kinematics we also define vectors representing another fundamental mathematical description of physical quantities, which are determined by a magnitude in a given unit and a direction like the velocity of a moving body. They are frequently visualized by arrows in a graphical representation, and the parallelogram rule holds for their addition. Tensors provide the most general mathematical description of physical quantities which involve not only magnitudes and directions but also planes in space associated with the action of tensors interpreted as linear maps between vectors or between vectors and scalars. As in the case of vectors, tensors can also be expanded in some basis constructed from a set of vectors in the Euclidean space. For example, by choosing the coordinate basis of the mutually orthogonal unit vectors EI defining the Cartesian coordinate axes, where the index I runs through the coordinates x, y, and z, we can evaluate the moment of inertia tensor I at the basis vectors, obtaining the matrix elements I sub ij in the given Cartesian coordinate basis. As a result, the basis expansion of the symmetric second-order tensor I can be written as the sum of the matrix elements I sub ij times the tensor product of the basis vectors ei and ej where the indices I and j run through the coordinates x, y, and z, and the basis expansion of the tensor provides the symmetric matrix representation of the tensor which is applied in computations involving the tensor. The basis expansion of vectors and tensors and the formula expressing the angular momentum by the product of the inertia tensor and the angular velocity vector clearly show the following. If the components of the angular momentum L and the angular velocity vector omega are determined in a fixed coordinate system in space, then the components of the moment of inertia tensor depend on time. This is due to the fact that the angular momentum of a force-free top has constant components in a coordinate system at rest, whereas the components of the angular velocity are time-dependent in the rest frame. For the product of the moment of inertia matrix and the angular velocity vector to be constant, the elements of the matrix must depend on time. However, in the principal axis system which rotates with the top spinning about an instantaneous axis, the products of inertia of the body, that is the off-diagonal elements of the moment of inertia matrix, vanish, and the right-hand side of the component equations of the angular momentum L of the body reduces to the terms containing the principal moments of inertia, that is the diagonal elements of the moment of inertia matrix. Namely, the component of the angular momentum L parallel with the principal axis A is equal to the product of the principal moment of inertia IA and the component of the angular velocity omega parallel with the principal axis A. Similarly, we can write that LB is given by IB times omega B for the principal axis B, and LC is equal to IC times omega C for the principal axis C. It follows from this result that the angular momentum and the angular velocity vector of the force-free top have the same direction only if the angular velocity vector points in the direction of any principal axis of inertia of the top. In such a case there is only one non-zero component of the angular momentum and the angular velocity vector in the principal axis system. If the direction of the angular momentum and the instantaneous direction of the angular velocity vector of a force-free top are the same, then the law of conservation of angular momentum stating that the angular momentum of the force-free top is constant, involves that the angular velocity vector of the top is constant as well. Hence the direction of the axis of rotation does not change in time for a force-free top. We conclude that only a principal axis of inertia can be a free axis of rotation. Now we can use these results to describe the motion of a force-free symmetric top qualitatively. By definition, the principal moments of inertia IA and IB are equal for a symmetric top, therefore all the axes passing through the point O in the plane spanned by the principal axes A and B are equivalent. This means that the equations describing the components of the angular momentum L of the top parallel with the principal axes A and B are the same, and we have only two independent equations stating that LA is equal to I times omega A, and LC is given by IC times omega C. Let us suppose that the angular velocity vector omega of a symmetric top, that is the axis of rotation, and the symmetry axis C are in the plane of the figure at a given instant of time. Since the axis A has an arbitrary direction in the OAB plane, we can choose this axis so that it also lies in the plane of the figure. Then we can decompose the angular velocity vector omega of the symmetric top with respect to its principal axes A and C, obtaining the components omega A and omega C parallel with these axes. Now the two equations describing the angular momentum L of the symmetric top show us that the vector L is also in the plane of the figure, which has a decomposition with the components LA and LC. Due to the law of conservation of angular momentum for a force-free symmetric top, its angular momentum L is a constant vector, that is, its position is fixed in the plane of the figure. At the same time, the axis of symmetry C leaves the plane of the figure as it rotates about the angular velocity vector L. Because the direction of the axis of rotation of the force-free symmetric top is instantaneous, the angular velocity vector omega also leaves the plane of the figure. The motion of the axis of rotation given by the angular velocity vector omega and the axis of symmetry C can be studied in simple experiments with spinning symmetric tops. The observations in such experiments demonstrate that both the axis of rotation and the axis of symmetry move on conical surfaces with the same angular velocity about a common axis given by the angular momentum L, which remains constant in space but changes its direction with respect to the body. Consequently, in the motion of a symmetric spinning top, three axes play an essential role. The axis of symmetry C, directly visible from the shape of the top, the instantaneous axis of rotation pointing in the direction of the angular velocity vector omega, and the axis pointing in the direction of the angular momentum L, which is not directly visible. These findings can be summarized as follows. The axis of symmetry of a force-free top and its axis of instantaneous rotation moving with constant angular velocity describe two circular cones about the axis of the angular momentum of the top, which is a constant vector in space so that the three axes always lie in the same plane. This general motion of the force-free top is called nutation, where the conical surface on which the axis of symmetry C moves about the fixed axis defined by the angular momentum L of the spinning top is the cone of nutation. The other conical surface on which the instantaneous axis of rotation moves about the angular momentum vector is known as the space cone. Under special initial conditions, the three axes coincide, that is, the nutation is simplified to a rotation around a free axis. In this case, we can talk about a nutation-free spinning top. In addition to the cone of nutation describing the motion of the axis of symmetry and the space cone at rest with respect to the space, we also show the body cone at rest with respect to the top describing the motion of the axis of rotation about the axis of symmetry C of the top. The space cone and the body cone touch each other along the instantaneous axis of rotation defined by the angular velocity vector omega, and we can interpret the motion of the top as the body cone rolling on the space cone. In reality, due to friction at the point O of support, the angular velocity of the nutation and the angles that the axis of symmetry C and the axis of rotation make with the axis of the angular momentum slowly decrease. After having a discussion on the motion of force-free spinning tops, we consider such cases where the external forces exerted on a top produce a non-vanishing net torque. If the center of gravity of the symmetric top shown in the figure is moved above the point of support O by shifting the weight attached on the rod of the top, gravity as an external force acting on the body produces a torque on the top. Such a top is simply called heavy spinning top. The figure shows a heavy spinning top that is rapidly rotated about its axis of symmetry C and placed on the stand at the point of contact O with a tilted axis of rotation. The weight of the top given by the product of its mass m and the gravitational acceleration g produces the torque tau at its center of mass C. In such a situation, the heavy spinning top does not fall down from the stand, but as it spins about its axis of symmetry C with the angular velocity omega c, the axis deviates in the direction perpendicular to the line of action of the force applied on the top, and moves on a conical surface with a vertical axis. This motion of the heavy top, which is well known in the case of the humming top, is called precession. Here the vector omega p pointing upward is the angular velocity vector of the precession. According to more precise observations, precession is usually not regular. If the initial spin of the heavy top is not very fast, or if we wait until the angular velocity omega c of the rotation around the axis of symmetry C becomes smaller and smaller due to friction, then noticeable fluctuations are also added to the motion of the axis of symmetry on the conical surface. The smaller the angular velocity omega c, that is the slower of the rotation of about the axis of symmetry C, the larger and slower these fluctuations. The axis of symmetry of the heavy top therefore usually performs the motion shown in the figure, and only in the case of sufficiently fast spinning the motion will become apparently regular or pseudo-precession, when the very small and rapid fluctuations of the axis cannot be detected by ordinary observation. With a suitable initial push of the top, fully regular precession can also be achieved. The explanation of this motion is based on the law of conservation of angular momentum, stating that the time derivative of the angular momentum L of a rotating rigid body is equal to the torque tau produced by the net force acting on the body. Because the torque does not vanish for a heavy spinning top, the angular momentum of the top is not constant but a time-dependent vector. In order to study the time evolution of the angular momentum, we will consider a fast spinning top whose angular velocity omega c of the rotation about the axis of symmetry c is much greater than the angular velocity omega a of the rotation about the principal axis a perpendicular to the axis c resulting from the initial push of the top. Since the spinning top is symmetric, the axis a is an arbitrary axis passing through the center of mass c of the body that is perpendicular to the axis of symmetry c. We already saw that the angular momentum L has the decomposition in the principal axis system of a symmetric top with the component L given by the product of the principal moment of inertia Ia and the angular velocity omega a, and the component Lc given by Ic times omega c. In the case of a flat top, where the principal moment of inertia Ic is greater than the principal moment of inertia Ia, we can establish that the component of the angular momentum L along the axis c is much greater than along the axis A. In other words, for a fast spinning top, the axis of the angular momentum and the instantaneous axis of rotation given by the angular velocity vector approximately coincides with the axis of symmetry of the top. By applying the equation describing the law of conservation of angular momentum, we can write the infinitesimal change in the angular momentum L over an infinitesimal interval of time as the product of the torque tau and the interval of time dt. For small but finite change, we have the equation stating that delta L is equal to tau times delta t. This expression is illustrated in the figure, where the value of the vector L plus delta L is determined by the vector addition of the angular momentum L and the change delta L given by the vector tau times the scalar delta t. Then we can state the theorem that the angular momentum of a heavy spinning top gradually changes so that it aligns in the direction of the torque produced by the gravitational force acting on the top. We assume that the vector L parallel with the axis of symmetry c is in the plane of the figure at the time t, while the torque tau is perpendicular to the plane of the figure and points inward. The condition that the angular momentum and the torque are perpendicular to each other is the consequence of the fact that the torque as a vector quantity is the time derivative of the angular momentum vector. We have seen that over the interval of time delta t, the angular momentum L changes in the direction given by the vector sum of L and delta L, which is gradually aligned in the direction of the torque pointing inward. As the figure shows, the component of the angular momentum L in the horizontal direction is equal to its magnitude times the sine of the half angle theta of the cone. If delta phi is the polar angle swept through by the axis of symmetry c and the angular momentum vector over the small interval of time delta t, then the magnitude of the change delta L in the instantaneous angular momentum can be approximated by the magnitude of the angular momentum L times sine theta, times delta phi. Because this change delta L in the angular momentum is perpendicular to the angular momentum vector L, the magnitude of the angular momentum does not change over the small interval of time delta t. At the instant of time t plus delta t, the torque tau of constant magnitude is already perpendicular to the vector L plus delta L, and as a result, the axis of symmetry c turns through the angle delta phi over the next interval of time delta t, and so on. This indicates that the vector of the angular momentum really moves along the cone with the angle at its apex and the fixed point O shown in the figure, and the heavy spinning top performs a precession. Heavy spinning tops usually perform a pseudo-precession since, as stated above, the axis of symmetry and the axis of rotation do not perfectly coincide with the axis defined by the angular momentum vector. Instead, they essentially perform nutations about the angular momentum vector, as already described in the case of the force-free spinning tops. These nutations contributing to the precession result in the motion of the axis of symmetry shown in the figure. In the case of fast spinning tops, the nutations can be neglected and we can determine the angular velocity omega p of the precession given by the ratio of the angle delta phi to the interval of time delta t. We already saw that the magnitude of the change delta L in the angular momentum is equal to the magnitude of the angular momentum L times sine theta times delta phi, which can also be written as the magnitude of the torque tau times the interval of time delta t. Then the ratio of delta phi to delta t is given by the magnitude of the torque tau over the product of the magnitude of the angular momentum L and sine theta. If dc is the distance between the center of mass c of the spinning top and the point of support O, then the lever arm of the torque tau is given by dc times sine theta, and the magnitude of the torque tau produced by gravity is equal to the mass m times the gravitational acceleration g, times the distance dc times sine theta. For a fast spinning top, the magnitude of the angular momentum L is practically equal to its component parallel with the axis of symmetry c, which is given by the product of the principal moment of inertia c of the top and the angular velocity omega c. Consequently, the angular velocity omega p of the precession of a heavy spinning top is given by the ratio of the magnitude of the torque tau produced by gravity to the product of the component of its angular momentum L parallel with its axis of symmetry c and the sine of the half angle theta of the conical surface on which the angular momentum vector moves. The angular velocity of the precession is also equal to the mass m of the heavy spinning top times the gravitational acceleration g times the distance dc between the center of mass c of the top and its point of support O, over the principal moment of inertia c of the top with respect to its axis of symmetry c times the angular velocity omega c of the rotation about the axis of symmetry c. This formula shows that the speed of the precession is proportional to the distance between the point of support and the center of mass, and inversely proportional to the principal moment of inertia with respect to the axis of rotation. The precession of heavy spinning tops can also be studied, for example by performing experiments with a spinning top suspended from a thread at the point O as seen in the figure, or with a Fessel-type gyroscope shown in the photo. In the case of the latter apparatus, the arm holding a flywheel rotating freely inside a ring or gimbal is balanced by a counterweight that is fit on the arm extending further than the pivot point O of the gyroscope. When the instrument is balanced, it works as a force-free or torque-free top. The torque is produced by the force of gravity acting on the way, and it can be modified by shifting the weight along the arm of the gyroscope. The spinning top or the gimbal rotates about its axis of symmetry c, and here we show the component of the angular momentum L parallel with this axis. The angular velocity vector omega p determines the axis and the speed of the precession of the spinning tops in the two experiments. The gravitational force given by the mass m of the spinning top or the weight, times the gravitational acceleration g produces the torque tau at the point of suspension or the pivot point O, which points inward in the case of the spinning top and outward in the case of Fessel's gyroscope. The component of the angular momentum L parallel with the axis of symmetry of the spinning top in these experiments is given by the product of the principal moment of inertia c of the top with respect to its axis of symmetry c and the angular velocity vector omega c of the rotation about the axis of symmetry. We already saw that for a fast spinning top the angular momentum vector L is approximately the same as its component LC pointing in the direction of the axis of symmetry. In both the experiments, the axis of symmetry of the spinning top and its angular momentum point in the horizontal direction. That is, the spinning top in the first experiment performs a precession about the thread of suspension, where the axis of symmetry of the top rotates about the point O in the horizontal plane. Similarly, the gyroscope in Fessel's apparatus performs a precession about the vertical rod supporting its arm at the pivot point O, such that the arm rotates in the horizontal plane passing through the point O. In both the cases the cone of precession reduces to the plane passing through the point O, on which the axis of rotation and the angular momentum vector of the spinning top moves. We already determined the angular velocity of the precession omega p of the spinning top, and found that it is equal to the magnitude of the torque tau over the product of the component of the angular momentum L parallel with the axis of symmetry c and the sine of the half angle theta of the cone of precession. As a result, the magnitude of the torque tau produced by the gravitational force acting on the spinning top or the weight attached to the gyroscope can be written as omega p times LC times sine theta. The right-hand side of this equation has the magnitudes of the vectors omega p and LC, and the half angle theta is the angle between the two vectors, which is a right angle since the cone of precession is reduced to a horizontal plane in these experiments. Motivated by this fact, we generalize this equation and state that the torque tau can be expressed by the cross product of the angular velocity vector omega p of the precession and the component vector LC of the angular momentum L parallel with the axis of symmetry c of the spinning top. This general equation also holds since the direction of the cross product in this equation is the same as the direction of the torque tau. Consequently, a fast spinning top rotating about its axis of symmetry c with the angular velocity omega c performs a precession about the angular velocity vector omega p, and the torque tau required to maintain this precession is given by the cross product of the vectors omega p and LC. This expression is equal to the principal moment of inertia c about the axis of symmetry c of the spinning top, times the cross product of the angular velocity vector omega p of the precession and the angular velocity vector omega c of the rotation about the axis of symmetry. Torque can be exerted on the spinning top not only by gravity or the earth, but it can also be produced by other forces or bodies. In the latter case, the body producing the torque is under the influence of a force exerted by the spinning top due to the law of action and reaction, which is called gyroscopic torque. That is, the spinning top produces the gyroscopic torque tau star on the body, which is equal to minus the torque tau. The torque exerted on the body that causes for the axis of symmetry of the fast spinning top to perform a precession with the angular velocity omega p, is then equal to minus the cross product of omega p and Lc, or minus Ic times the cross product of omega p and omega c. Here the torques tau and tau star relate to each other in the same way as, for example, the centripetal force and its reaction force exerted on the body that is constrained by a cord to move along a circular orbit. The gyroscopic torque tau star produced by a spinning top can be directly detected, for example in the case of Fessel's gyroscope, as the resistance of the arm of the gyroscope if it is pushed down with hand instead of the weight, or when the direction of the axle of a spinning bike wheel is changed. We can illustrate the latter example with a bicycle wheel that has two lead rings of the total mass m attached on its circumference, increasing its moment of inertia about its axis of symmetry c, which is also its axis of rotation. Let us hold the axle of the bicycle wheel spinning with the angular velocity omega c at the points P and Q in a horizontal position with both hands as seen in the figure. Then we try to rotate the axis in the plane of the figure about the center of gravity at the pivot point O to the left. This rotation represents the precession of the axis of symmetry with the angular velocity vector omega p pointing outward from the plane of the figure. Then the torque tau required for this rotation is given by the principal moment of inertia Ic with respect to the axis of symmetry c of the bicycle wheel, times the cross product of the angular velocity vectors omega p and omega c. This torque is produced by applying the force F pointing outwards perpendicular to the plane of the figure with our left hand and the force minus F pointing inwards with our right hand. Due to the torque of the bicycle wheel working as a spinning top, its axle exerts the forces F star and minus F star on our hands, which are opposite to these forces, pulling our left hand inwards and our right hand outwards. Because the vectors omega p and omega c are perpendicular to each other, the magnitude of torque tau and the gyroscopic torque tau star is equal to the principal moment of inertia Ic times the angular velocity omega c times the angular velocity omega p. If d denotes the distance between the points P and Q, that is the arm of the force couples, then the magnitude of the forces in the force couples is simply given by Ic times omega p over d. For example, let us consider a bicycle wheel of radius r that is equal to 0.35 meters, where the total mass m of the lead rings attached to the circumference of the wheel is equal to 10 kilograms. Let us also suppose that the frequency nu c of the rotation of the wheel about its axis of symmetry c is given by 3 per second, and the frequency nu p of the precession is equal to 1 per second. The latter can be achieved if we rotate the axle of the wheel into a vertical position over a quarter second. The principal moment of inertia Ic of the wheel about its axis of symmetry c is approximately equal to the mass m times the square of the radius r, that is 10 kilograms times the square of 0.35 meters, which is equal to 1.2 kilogram meter squared. The angular velocity omega c is equal to 6 pi per second and the angular velocity omega p is given by 2 pi per second. If we substitute these values into the equation of the magnitude of the torque tau, then we obtain 144 kilogram meter squared per second squared. For the arm d of the torque that is equal to 0.4 meters, the magnitude of the force couple given by the ratio of the magnitude of the torque to its arm is equal to 360 newtons. We can hardly exert such a strong force or torque on a body with our hands, so it is understandable that when we attempt to rotate the axle of the wheel, this reaction tilts our hands in the directions of the forces F star and minus F star. If we perform the experiment on a turntable, the reaction forces can even rotate the turntable. We have seen that the main properties of a spinning top are the stability of the rotation of the top about its free axis, the precession produced by the torque exerted on the top, and the gyroscopic torque produced by the spinning top when the direction of its axis of symmetry is rotated. These properties play an important role in the interpretation of many phenomena and are used in many applications. Here we mention some of these phenomena in nature and the everyday life and some applications in transportation and industry. One of the gyroscopic effects that occur in freely moving bodies is the precession of the Earth's axis. The shape of our Earth is not a sphere, but it can approximately be described as a rotational ellipsoid, and its axis of symmetry forms an angle of 23.5 degrees with the normal of the plane of the Earth's orbit, the ecliptic. Besides the gravitational force F exerted on the spherical part of the Earth at its center of mass c by the Sun, we need to take into account other attractive forces due to its oblate spheroid shape. The force F1 acting on the bulge part closer to the Sun at the center of mass c1 of the bulge part, and the force F2 acting on the bulge part farther away at its center of mass C2. In accordance with Newton's law of gravitational attraction, these forces point in the same direction, but the force F1 has a greater magnitude than the force F2. That is, the Sun exerts more attraction on the bulge part of the rotating Earth closer to the Sun than the bulge part farther away. Then the net force produces a torque exerted on the planet attempting to elevate the Earth's axis of rotation. The Moon also has a similar effect on the Earth. Due to the torque, the Earth's axis moves on a cone of precession of 23.5 degree half angle at its apex with a period of 25,800 years. Consequently, the positions of the intersections of the ecliptic and the celestial equator called spring equinox and autumn equinox also change. Furthermore, the role of the fixed star called the North Star or Polaris aligned with the Earth's axis of rotation will be taken over by another fixed star over time. The precession of the Earth's axis is also accompanied by periodic fluctuations as the torque changes due to the relative positions of the Sun, the Earth and the Moon. These astronomical notations are not to be confused with the generally smaller Chandler wobble, a free nutation that also occurs in the case of the Earth for the reason mentioned in the case of the heavy spinning top. In some cases, the unconstrained motion of a body is stabilized by applying a rapid rotation. For example, if a discus is thrown in a proper way, the direction of its axis of symmetry as an axis of rotation remains almost unchanged due to stability, despite the influence of air resistance. Therefore, in the second part of the orbit, the disk is in a position similar to that of the winged surface of the aircraft with respect to the direction of air resistance, and due to the buoyancy of the air, it flies significantly further than the distance corresponding to the parabola of a projectile. The axis of symmetry C of a cardboard disk, such as a beer cup coaster, no longer holds its direction due to the lower stability associated with a much lower moment of inertia with respect to this axis, but rotates under the influence of the horizontal torque produced by the air resistance. Then its axis of symmetry finally reaches a horizontal position, where the flying disk rotates in a vertical plane. In the case of a projectile fired from a gun with riffled barrel, which rotates around its longitudinal axis due to the helical grooves cut into the inner surface of the barrel, the axis performs a complicated precessional motion due to the air resistance that changes with the position of the projectile. As a result, its axis almost always points in the direction of its trajectory, so that the projectile hits the target with its tip but deviates sideways from the vertical plane of sight. An example of the gyroscopic effect that plays a role in stabilizing constrained movements can be seen in the case of cycling without handlebars. If for some reason, a cyclist moving fast deviates from the position in which his center of gravity is in the common vertical plane of the two wheels of the bicycle, for example the bicycle wobbles, then the force of gravity produces the torque tau on the front wheel as seen in the figure. Due to the torque tau, the axis of symmetry C of the wheel performs a precession, where the momentum L rotates about the axis of the steering wheel in the direction of L plus delta L, that is, the wheel turns in the direction of the wobble. In this way, however, the line connecting the points of contact of the two wheels with the ground will soon be in such a position where the vertical line passing through the cyclist's center of gravity will cross this line again, that is, the bicycle's original torque-free position will automatically be restored. The gyroscopic torque has effect on the motion and operation of other vehicles as well. Spinning tops were used to stabilize monorails and to dampen the vibrations of ships about their longitudinal axis by braking the motion of the ship's gyroscope weighing several tons. The straight-line movement of the fired torpedo is ensured by indirect stabilization. When the torpedo changes direction, the precession of a built-in spinning top activates a steering mechanism that restores the original direction. When the axis of rotation of bodies rotating fast such as motors and vehicle wheels changes its direction, large torque can be produced as a result of the spinning effect, as we have seen in the case of the axis of a bicycle wheel. For example, when a train turns in curved railway tracks, the rotation of the axle of its wheels about a vertical straight line results in a horizontal torque due to the effect seen in the case of the spinning tops, so that the compressive force exerted on the outer rail by the wheels increases, and the compressive force exerted on the inner rail decreases. This effect, together with the centrifugal force in the same direction, can lead to the overturning of the train. Similarly, if the axle of the wheels is tilted around a horizontal axis due to the deformation of one of the rails, it produces a torque in the vertical direction that may cause a derailment. When changing the direction of an aircraft, the pilot must take into account the gyroscopic torques of the spinning propellers, and on the other hand, the suitably installed spinning top can be applied as a detector of the rotation of the aircraft. Gyroscopic torque can also be used in mills to increase grinding pressure. The axis of symmetry of the two mill wheels rotating about a horizontal axle is connected to a vertical one by a hinged structure at point O, and rotates about a vertical axis. Hence, For example, the right wheel exerts the torque tau star on its horizontal millstone as seen in the figure, and the compressive force on the material placed between the wheel and the stone becomes significantly greater than the weight of the wheel. Let us summarize the content of this presentation on the dynamics of rigid bodies. We started with the discussion on the rotation of rigid bodies about a fixed axis, where we solved the equation of motion stating that the time derivative of the angular displacement of the rotating body is equal to the component of the torque parallel in the direction of the axis of rotation. Here the torque is produced by the external forces applied on the body. We considered different special cases where the torque either vanishes or it is constant. For vanishing torque we saw that the body rotates at a constant angular velocity, whereas in the case of a constant non-zero torque we found that the body rotates at a constant angular acceleration about the fixed axis. We derived the kinetostatic equations of a rigid body from the laws of conservation of momentum and angular momentum expressed in a coordinate system adapted to the axis of rotation. In the study of rigid body kinematics we already introduced the moment of inertia of a rotating rigid body with respect to its axis of rotation, and expressed the rotational energy of the body in the terms of this quantity and the angular velocity of the rotation. We generalized the moment of inertia of a rigid body with non-uniform density by the volume integral of the product of the density of the body as a function of position, and the square of the distance between the position and the axis of rotation. By applying this formula expressed in a Cartesian coordinate system adapted to the axis of rotation, we determined the moment of inertia several regular solids of uniform density. We also derived the moments of inertia and the product of inertia of a rigid body with respect to an axis pointing into an arbitrary direction in a Cartesian coordinate system. We proved the Huygens-Steiner theorem stating that the moment of inertia of a rigid body with respect to an axis is equal to the sum of its moment of inertia with respect to a parallel axis passing through the center of mass of the body, and the product of its mass and the square of the distance between the two parallel axes. This theorem was also applied to determine the moment of inertia of homogeneous regular solids with respect to non-central axes. The ellipsoid of inertia of a rigid body with respect to a given point of the body was introduced as well, where the moment of inertia of the body with respect to any axis passing through that point is determined by the distance between the point and the ellipsoid in the direction of the axis. The axes of symmetry of the ellipsoid define the principal axes of the inertia, and the moments of inertia in the direction of these axes are the principal moments of inertia of the rigid body with respect to that given point. We showed that in the principal axis system of the body, that is in the Cartesian coordinate system adapted to the principal axes of inertia, the moment of inertia with respect to the given axis reduces to a simple expression in the terms of the principal moments of inertia, while all the products of inertia vanish. We used this simple form to write the kinetic energy of a rotating rigid body as 1/2 times the sum of the products of its principal moments of inertia and the square of the components of the angular velocity vector of the rotation in the direction of the principal axes of the body. Then we presented two types of pendulums, the torsion pendulum and the physical pendulum, and described their operation. The operation of a torsion pendulum is based on Hooke's law of torsion stating that the torque trying to restore the equilibrium position of the pendulum rotated about a vertical axis is directly proportional to the angle of rotation, where the constant of proportionality is the torsion constant of the pendulum. This constant appears in the equation of motion of the pendulum, and its ratio to the moment of inertia of the pendulum gives the square of the angular frequency of its oscillation about its vertical axis. A rigid body is called physical pendulum if it is free to rotate about a fixed, horizontal axis under the influence of gravity. By transforming its equation of motion, we proved that a physical pendulum swings with the same period as a mathematical pendulum of the reduced length of the physical pendulum for small oscillation. The reduced length of the pendulum is defined by the ratio of its moment of inertia with respect to its horizontal axis of rotation to the product of its mass and the distance between the point of suspension and the center of mass of the body. We also listed some special type of physical pendulums and applications from everyday life using such pendulums like mechanical metronomes, pendulum clocks, reversible, balanced and horizontal pendulums. Then we moved on to the topic on the motion of a sphere and a cylinder rolling down an inclined plane under the influence of gravity. We determined the instantaneous acceleration of these solids in the terms of their mass, radius, moment of inertia with respect to their central axes, and the angle of inclination of the plane. We wrote the kinetic energy of the rolling bodies as a function of their geometric and physical properties. We also examined the effect of the rolling friction between the bodies and the inclined plane in their motion. We established that the frictional force and the torque produced by this force reducing the angular velocity of the rolling bodies can be approximated by the product of the coefficient of rolling friction and the normal force pressing the body against the inclined plane. This coefficient can be determined by finding the angle of inclination of the plane at which a body rolls down with uniform velocity. As a next topic, we studied free rotations where a rigid body rotates about an axis that is not fixed. We presented some experiments illustrating that the principal axes of inertia of the body with respect to the center of mass of the body are free axes. We found that the free rotation is most stable about the principal axis with the greatest principal moment of inertia. The free rotation is still stable about the axis with the smallest principal moment of inertia, but unstable about the axis with the intermediate value of the principal moment of inertia. Then we talked about the rotation of force-free spinning tops where the torque produced by the net forces acting on the top vanishes. We saw that the angular momentum of a rotating body expressed as the matrix vector product of the moment of inertia matrix of the body constructed from its moments and products of inertia, and the angular velocity vector describing the speed of the rotation and the direction of the axis of rotation. This expression was also applied to write the kinetic energy of the rotating bodies as 1/2 times the dot product of the angular velocity vector, and the matrix vector product of the moment of inertia matrix and the angular velocity vector. As a special case of this formula applied in the principal axis system of a force-free top, we proved that the angular momentum and the angular velocity vector of the top have the same direction only if the angular velocity vector points in the direction of any principal axis of inertia of the top. We studied the nutation of force-free tops, where the axis of symmetry of the top and its instantaneous axis of rotation moving with constant angular velocity describe two circular cones about the axis of the constant angular momentum vector of the top so that the three axes always lie in the same plane. We finished this presentation with the discussion on heavy spinning tops where the torque produced by the external forces acting in the top, normally gravity, does not vanish. For a fast spinning top, we saw that the axis of the angular momentum and the instantaneous axis of rotation given by the angular velocity vector approximately coincide with the axis of symmetry of the top. Heavy spinning tops rapidly rotating about their axis of symmetry perform precession, where the axis deviates in the direction perpendicular to the force acting on the top and moves on a conical surface with a vertical axis. We also concluded that heavy spinning tops usually perform a pseudo-precession since the not completely coincident axes of the symmetry and rotation perform nutations about the axis defined by the angular momentum vector of the top. We determined the angular frequency of the precession as well in the terms of torque, the angular momentum and the half angle of the cone of precession. We found that the gyroscopic torque produced by the reaction force of the heavy top is equal to the principal moment of inertia of the top with respect to its axis of symmetry, times the cross product of the angular velocity vectors of precession and rotation. We mentioned some of the natural phenomena and applications in the everyday life as well where the effects related to spinning tops are important, such as the precession of Earth's axis, the behavior of rotating disks and projectiles flying in the air, and the wheels of vehicles or crushing mills.